Let's see if this is working. Let's give this a shot. So yeah, today I'm gonna try to do 8 hours of programming and see how far we get. Just make sure it's working. Do 8 hours of programming and see how far we get. My hair's a little messy today. Do 8 hours. Alright, so first question is going to be counting words with a given prefix. Let's take a look. Just give me one moment. Here we go. Okay. Yeah, I think my hair is maybe a little bit. I might need a haircut. Alright, given an array of strings words and a string prefix, return the number of strings and words that contains a prefix as a prefix. Prefix of a string is a leading contiguous substring of S. Okay, this is a pretty straightforward one. So we're just going to say const auto check prefix. Write a subroutine for this. It's going to be prefix. This should also be by reference. This should be a string. And we're going to say for loop. So we're going to say bool check equals true. Return check. Actually, just return true. Should be it. And then we're going to say int I is 0, I is less than prefix dot size. I is less than s dot size. Let's say if prefix of I is not equal to s of I, and return false. In this case, we could write our own custom check prefix. And then we can have return stood accumulate of, I have a few things. It's going to be words begin, words end. Words begin, words end, 0, and then this subroutine. It's going to call check prefix with prefix and const string this and accumulate. And we're going to say return accumulate plus check prefix of s. I think that's it. I think that's what we need. Let's see. Let me just check and see that the stream is working fine. How's my hair look? I think it's let's see. Let me just. I'm not sure. How's my hair look? I think it's let's see. It's a little messy. I need a haircut. I definitely need to get a haircut. But the stream is okay. Stream health. Let me go ahead and continue with the problem. So it looks like that was the right way to go. Let's give it a shot, see how it goes. I'm gonna do it on time also. I'll let that take a few minutes. Oh, it's wrong. No. Oh, that's brutal. Okay. Ooh, output 1 expected 0. Ooh. Oh no. I made an error here. There was a slight error here. I knew I was taking a small risk writing this custom code. I forgot something very subtle here. It's important. If this string is smaller, yeah. So it's gonna be pref.size has to be less than or equal to s.size. That's what I missed. I thought I got that case, but I didn't think it all the way through. That was my mistake. I like thought I got it, but I didn't get it. Yeah, that was my mistake. That's subtle. Yeah, that was bad on my part. Let's submit it one more time so I don't feel as bad. Um, oof. Okay. Yeah. I don't know what to say about that. I have no excuse. No excuse for that. I thought I got it, but I didn't think hard enough about that one. Very slight thing. In a square matrix mat, return the sum of the matrix diagonals. Only include the sum of all the elements on the primary diagonal and all the elements in the second diagonal that are not part of the primary diagonal. Sum of the matrix diagonals? Primary diagonal, secondary diagonal. Oh, okay. That's it. Alright, that's not too hard. So sum of the diagonals is pretty straightforward. It's just going to be int result 0. Oh, let's just double check that this fits the constraints. Only 100 by 100. Yeah, it's going to fit an int. It's fine. Okay, so it's going to be I0. It's less than square 2 dot size plus I result plus equals mat of I, and then the other direction, which is almost the same thing. So this one, it starts off the row and the column increment in the same direction. This one, you just go in the other direction. So the row is still I, but the column is n minus I think minus 1. Double check if it's minus 1 or not. Where n is mat size. So it's going to be the first row, but the last column, which is mat size minus 1, and then I is 0. So yeah, so it should be this one, I think. I think this. Oh, it's wrong. Oh, shoot. Okay. 30, 25. What is, it should be 1. Oh, but you only add, oh, the middle element shouldn't be added twice. Okay. No, there's a slight mistake here. And that's because they're adding the middle element twice. So if mat.size and 1, if it's odd, then we're going to say result minus equals mat.size, the middle element, which is like mat.size divided by 2, I think. We're going to bit shift 1. Actually, it's bit shift to the right one, not left. I think we subtract that. That's kind of subtle too. It's a good thing I didn't submit that. Yeah, that's a subtle thing. Let's see. Yep. Okay. We'll submit it again so I can just double check the time and the stream health. Also, take a look at my hair again. The stream is healthy. I'm not each time I touch my hair, I kind of maneuver it around a bit. Yeah, it looks okay. So 9 minutes. 2 questions in 9 minutes is okay. I'm trying to keep track of like how quickly I could solve these, because I should be able to solve them kind of fast. That one's not a very tough one. And none of these are really that tough. This one's solved already, so we'll just quickly explain it. Okay, constructing the binary search tree from a pre-order traversal. This is a tricky one. Basically, a pre-order traversal is going to give you the initial node, then the left subtree, then the right subtree, and it recursively. So then that left subtree, for example, is going to be the initial node, the root node, and then another split into left subtree and right subtree. So the way this would work is in order to to reconstruct the binary search tree, you would have the root, and then you'd have somewhere to the right is going to be so the first root, then the left subtree is going to have the next element is going to be the root of that node, that tree, and then somewhere to the right is going to be the root for the right subtree. The tricky thing here is it's not clear where the right subtree begins. Excuse me. So I think it's going to have to be, because of binary search tree, you can scope ahead basically and find where that right subtree is going to be. And then you can create then you could basically recurse on that element. I think it's still linear time if you do it this way, even though you're doing this sort of these extra steps of like kind of going over to the side. The reason why I think it's fine to do that is because you're only, when you move over to the right to find the next element, like the next subtree, I think you only ever move further to the right. So like when you recurse on that right subtree, for example, the left subtree starts immediately to the sides. There's no cost, there's a constant cost there. And then when you recurse again on the right subtree, you're only going to keep going to the right further. So because even though you do a significant amount of work moving to the right initially, or at least when you first find that right subtree, the overall amount of work over all of those subtrees is going to be at most linear, so it's amortized linear, or amortized constant, basically, over all those operations. So you can do that just fine. So basically you can just root node is the first node, next element is the left subtree root node, recurse, not exactly recurse, but almost recurse. Before you recurse, scan to the right until you find the first element that's larger than the root node. That's going to be the beginning of that's necessarily going to be the beginning of the right subtree because it's a pre-order traversal, which means that that element is always going to be, that first element is always going to be the root of that right subtree. I think this is correct. I think you can do it this way. I could be wrong, but I think that's the way to do it. I've solved this already, so at some point in my life I knew the answer. But we're gonna skip it. I think that's the way to do it. But that's how I would do it now if I did it again. Okay. So, but that's, I think, the way to do that. I'll maybe come back. Maybe at some point I'll come back and try it again. Pangram is a sentence where every letter of the English alphabet appears at least once. A sentence string containing only lowercase letters turn true to pangram, false otherwise. Okay, true or false. So this is a pretty straightforward one. Basically, just use a full frequency or has letter, right? And make this empty initially. Fill this letter. False. For const char ch in sentence. It's also turn int count 0. Actually, we could even, I mean, just thinking, how big are these? I think we want to optimize this a little bit. 1,000. Okay, no, that's fine. We'll just keep it simple. So we're gonna say has letter of ch minus a or equals with true. I think we just set it to true actually, and then return stood accumulate of has letter this letter plus 26. 0 equals greater than equal to 26. Something like this. I think it'd just be equal to 26 is fine, but something like this works, I think. Let's try this. Yeah, I think that's it. Let's go for it. Yeah, very straightforward. Just basically save in a like a Boolean set of bools, like array of bools, of whether or not those characters are there or not. Cells in a range on an Excel sheet. Cell row column of an Excel sheet is represented as a string. Column row. Interesting. Where column denotes the column number C of the cell is represented by alphabetic letters. The first column is denoted by A, second B, and so on. Row is the row number of the cell. So given a string S, the format column 1, row 1, column 2, row 2. Can you give me an example? Column row represents such that R1, R2. Okay, so it's going to give you like a subsection of a grid. The list of cells such that this is true. The cell should be represented as strings in the format above. Be sorted in non-decreasing order first by columns, then by rows. Sorted in non-decreasing order first by columns and then by rows. Oh, okay. Column and then row. Oh, that's interesting. It's a column row order. It's a little bit unusual, but yeah, it's kind of somewhat inverted. But so column and then row. Okay. Usually it's row column. So K1, K2, L1, L2. Okay. Column and then row. All right. Huh. Interesting. So it's going to give you kind of a subsection, and then we got to do column row list. All right. A little odd, but I think I can handle this. Can also let's just see. Okay, it's between A and Z and 1 and 9. All right. Interesting. So constant row 1, R1, or K1, or C1. It's going to be CS of 0 minus A. C2 is, I think 3, 0, 1, 2, 3. Yeah, 3. R1 is R2. It's 1 and 4, I think. And this is minus 0. These are characters. So, yeah. Second one is the row, and then third, fourth, fifth, the fifth characters. Right. Okay. A little bit confusing, but so we're just going to convert. So we're going to say for int row equals R1. Actually, we should do column. Yeah, column order. Column C1, C2, column, row, R1, rows listed with R2, row, and then return results. And this is going to be result.observe. It's going to be, I think, the R2 minus R1 times C2 minus C1. I think that's how many elements I need. think that's right. And then we're gonna use so we've got to convert these strings. So result.pushback. A string, like, it's gonna be good std move maybe. Is it std string? I'm not really sure actually. Can I construct a string this way? I could try. So I wonder about this. I don't know. String. Let's just say next, or we'll just call it S. Not really sure. I'm gonna move it anyway just to see how this goes. So the column comes first and the row comes next. The column character is going to be plus A, I think. I have to think about this a little bit more. And then the row is going to be +1. Or I think just +0. It's something like this. I gotta think about it a little bit. What's up? Hello, how old are you? And what's your background and current situation in tech? Hello, sir. What's up? Nico, Rocket League, welcome. Howdy. I'm in my 30s. My background, I worked on algorithmic trading systems for the corporate world. Did like client services for buy-side equities. And current situation in tech, I'm currently looking at, so I have a degree, TA'd a course in computational geometry when I was younger. Worked about almost 4 years in the corporate world. I've been programming for like 20 years, like since I was a kid. Almost 20 years. On it, not working currently as a developer though, because I'm kind of in a weird place in life. I've been looking more at like doing mentorship, tutoring, and or coaching, and doing making some YouTube videos. At the moment, and yeah, at the moment. I don't work in tech explicitly. At the moment, I do. I just work in fast food at the moment, which is pretty easy. Or I shouldn't say it's easy. It's different. It's a little easier than tech, in my opinion. Runtime error out of bounds. Undefined behavior. UB. That's unusual, huh? Index 75. Const char. What did I do here, huh? I might need to think about how I want it. I don't want to use a string stream for this, but that's one way of doing it. I mean, I could do it this way too. This is probably easier. There's a few ways to do this, I think. Let's try this. Let's see what this does. This may not be the best way to do it. I'm sure there's better ways to do it. There's like, yes, there's like subtleties of string manipulation that I'm like not super familiar with. Yeah, there we go. Straightforward. That works. I mean, this wasn't the best solution because it just took a while to program. It's reasonable, but it's like not the best. All right, how are we doing on what's the health of the stream? Okay, not just buffering a little bit, I think. Okay, let's just give it a moment to stream health buffering. Also, what's the health of the stream? Okay, not just buffering a little bit, I think. Okay, let's just doing better now. All right. Sweet. So yeah, I mean that's an okay solution. But yeah, I mean, as far as employment, like the last recruiter I spoke to, they were looking at, um, well, I mean, I shouldn't get into all that. Like the roles that I apply for now, some of them pay like 350,000 a year. Some of them pay like 500,000 a year. But I'm kind of not too excited about those roles for various reasons. Final prices with a special discount in a shop. You were given an integer array of prices where prices of I is the price of the ith item in a shop. There's a special discount for items in the shop. If you buy the ith item, then you will receive a discount equivalent to price of j, where j is the minimum index such that j is greater than I. And prices of j is less than or equal to prices of I. Otherwise, you will not receive any discount at all. Return integer array answer, where answer of I is the final price you will pay for the ith item in the shop, considering the special discount. Okay. Item 0 price, receive a discount from the prices of 1, 4. A minus 4 is 4. What is the... Okay, we get the integer array, special discount, ith item, equivalent to price of j, the minimum index such that j is greater than I, and price of j is less than price of I. Otherwise, there's no discount. So there's got to be some element to the right. How many elements are there in this array? This is like kind of a look ahead question. Okay, it's only 500. So, I mean, we could do a very basic approach. It's the first element to the right that's smaller, basically. I mean, a look ahead's fine. I'm wondering if I should use a stack to do this. Might be easier, more efficient. A brute force solution is fine here. Like you just look ahead for each element, but a stack-based solution, basically you push the element when you see it. Then when you see an element that's smaller, you pop everything from the stack that's larger, and then push the smaller element on. Yeah, that's the way to do it. Stack works nice. Excuse me. Stack's pretty solid here. So stood vector result. Reserve prices of size. Then we're gonna have a for loop. We have a stack. I'm gonna use a vector as a stack. Same deal. Then return prices. We're gonna say we can just do this. Prices.size. You can actually even go further. You can do it like this. X and prices doesn't really matter. So I'm gonna say for st.top is greater than x. Then we're gonna pop. So st.notEmpty. And then we're gonna say the following. St.pop. We're gonna say result.pushback st.top minus x. Right? Push and pop. And then st.push back. It's because I'm using vectors, it's gonna be back. Pop back. Yeah. And then st pushback x. Something like this, I think is what we want. wrong. Okay, what did I do wrong? I'll put 8. So we have X as the price. ST is empty. So we skip, push X, which is 8, onto the stack. Then we see 4. And then we say, okay, the stack, which has 8, it's not empty. It has 8 is greater than 4. We're going to push on the result. We're going to push 8 minus 4. So we should have pushed 8 minus 4. Oh, I returned prices. That's why. Excuse me, should return result. That's okay. I was like, where is my logic wrong here? What did I do? Oh, it's wrong though. Okay. 442. Should have been. So push the 4, we pop 8, then we push 4 onto the stack. Oh, I see the issue. Then we push 6 onto the stack, I think. Oh, you know what? It might be, it maybe should be a queue, actually, not a stack. Yeah, I think I was supposed to push 4 minus 2 before I push. If I do it this way, I'll push 4 and 2, not 2 and 4. It'll be the wrong sequence, but also it's I see what I'm missing here. Okay, that's subtle. So 4 that's the empty. Pop. So that's actually, I can't, so I did slightly incorrectly. And just, I think I need to dump the rest of the elements in there. So I do need to use more like a queue than a stack. Yeah, these are gonna be in the wrong orders. Okay. Okay. Interesting. So what's interesting about this is that I don't think I need to use a queue necessarily, because this is gonna always be a max. Oh no, it's correct. It's just I just need to reverse this, that's all. It's a bit awkward. Yeah, it's a little awkward. We're gonna do it like this. This is a little awkward, but I think this is right. Yeah. Okay, so we're gonna do the following. And then we dump this into the result. It's actually gonna be more like this. Yeah, it's a little awkward. It's a little awkward. Something like that. Let me see. What does this do? Wrong. Okay, hold on. Okay, yeah. So I did do this middle part correctly, but the last part's just slightly incorrect. Um, just the same thing as this here. Um, just let's see. Okay, still wrong. Oh, these are not supposed to be reversed. Is that it? Okay, a little bit better. There's something wrong here. Oh, I think they. Oh, less than. I'm sorry, that's my mistake. Um, no, I'm sorry, but I shouldn't say. I've been saying I'm sorry a lot lately because I have coworkers that are very. Oh, I shouldn't say that either. I shouldn't say that either. I've been working lately, and I apologize a lot to my coworkers because I don't know what else to say, quite frankly. I don't know what to say. I don't want to upset my coworkers, so I just apologize constantly. It's just easier to do it that way. I think. I don't know if it's easier to do it that way. I have no idea. This seems to be correct, but I'm not sure this is the best way to do this. It's wrong. It's not correct either. Of course it's not. I might be trying a little too hard on this one. The the approach I described earlier would be sufficient for the time balance, and I probably should just use that one. But part of me feels like I should try to do something a little more sophisticated here. I'm surprised this is wrong. Um, hmm. What happened here? Okay. So I had the 1 here. 9, 4. Hmm. Mm, you know what? There is actually a better way to do this. This is just wrong. I think. Hold on. Let's go back to the drawing board here. Actually, I had the right idea the first time around. I just didn't think it all the way through. So I did actually, not that I did it correctly the first time, but I was close the first time. Uh, I think I know what I'm doing wrong here. So what it's supposed to be is the indices, I think, in this stack. Um, so I do need to do, yeah. Okay. Let me do it this way. In this case, we can do something like the following. All right. Stack is empty, stack back. So it's going to be still going to have a stack, but it's going to be a stack of indices. So it's going to be prices stack back. And then we're going to not push back, but we're going to write to the index. The result of st back is going to be equal to prices. Yeah, this I think is what I was supposed to do. Initially, I just kind of didn't think it all the way through, I guess. And then we push X back on the back of the stack. Yeah, I think this is what I'm supposed to do. It's supposed to be index based. And then I just write the indices at the end. So yeah, it's just gonna be pushback, not pushback, but result of the index to the pointer. And then we do prices of, it's just gonna write basically this. Something like this. Let's see. Oh, and X is price of I. I could just do constant x. Specify. Yeah, I think I kind of goofed this. I kind of goofed this. Okay. Buffer overflow. Okay. Of course. Oh no, not push X. Whoops. Push I. That'll do it. Yeah, that'll cause buffer overflow. All right, there we go. That's correct. Yeah. I goofed, man. I goofed. I don't know what to say. I should have thought that through a little bit more from the beginning. It's more of index based kind of thing. Uh, yeah, I don't know, man. No excuses for that. No excuses for that. That's there's a few other problems that are similar to that. But yeah, that's a linear time solution rather than I don't know. Yeah, no excuses. No excuses. Find elements in a contaminated binary tree. So I've already solved this one. What are some of the things to say about this? It's also linear time memory, also that previous one. Binary tree with the following rules: root.val for any tree node. If tree node.val is value x and tree node.left is not equal to null, then tree node.left.val equals 2 times x plus 1. Okay. Tree node.val has a value x, tree node.right is not equal to null. It's 2 times x plus 2. Okay. So it starts off with 0. If it has a node on the left, it's going to be twice that plus 1. So it's going to be 1. Then the one on the right is going to be 2. Then the 1, if we repeat that, times 2 is 2, plus 1 is 3. On the right of that is, so it's going to be 0, 1, 2, 3, 4, 5, 6, and so on. So it's kind of like if it was a full tree, it would be like a level order traversal of like the natural numbers. Or yeah, level order kind of I don't know what the word is for that. Placement of the natural order of the natural numbers, starting from 0 rather than the natural numbers, the positive, non-negative integers, So integers including natural numbers including 0. Now the binary tree is contaminated, which means all tree node.val has been changed to -1. No, what? Implement the find elements class. Find elements initialize the object with a contaminated binary tree and recovers it. Find target returns true. The target value exists in the recovered binary tree. Oh boy. Uh-oh. Okay. Interesting. So I've got to recover. Huh. And then have the find routine. Interesting. Well, each of the finds can be done in binary logarithmic time. Logarithmic in the, I think the, not exactly logarithmic. I'm not really sure actually. The find is a little bit complex. Total number of nodes is 10,000. Total number of calls to find is 10,000. Height of the binary tree is less than or equal to 20. Okay, well, if it's the height is less than 20, then yeah, you can do the find can be linear in the height. But yeah, it should be linear in the height. The basic approach. So like I said, I've already solved this one, so I'm not gonna solve it again. But I'll just give a brief description of how you can solve this. So I would say I'm not sure it's really necessary to actually modify the tree. I don't know. I'm not sure if the way they program this is actually going to check that. Null, true, false, false, true. I don't know. I don't know if they don't bother to check whether or not I mean, the tree, it's not that hard to recover the tree. I mean, you could just do the whole thing. I guess it's fine. Um, so you would literally just recurse from the simple recursion is fine, and in order traversal is fine. So you would say, or you could do pre-order is fine too. So you would set the root node to 0, and then the left side and the right side, um, you would just save the so in the recursion you just have an integer that you parameter that you save, like what the next value is going to be. So starting from 0, you'd have 2 times 0 plus 1, and then the other one would be 2 times 0 plus 2, and so on. And so you can recurse that way. So yeah, pre-order traversal works fine. Recursive approach, and then that's if you had to write the new value, the correct values of the tree, and obviously if it's a null, you just skip it. If the tree denotes null, and then the find you would just run on the tree, left or right depending on what you're searching for. So, whether or not the value is going to be the left subtree or the right subtree is it's actually not that obvious where it's going to be. I'd have to think about that actually. What does the find routine look like? It's gonna be. Let's see if you had to find 5. Let's do something more complicated. Like, let's say you defined like it says 10,000 nodes. Let's say you defined like 5,000. So start off with 0. 5,000. That's actually a good question. How do you? Would you go to the left subtree or the right subtree for 5,000? Good question. Well, you have two options, right? You have either subtract 1 and divide by 2, or subtract 2 and divide by 2. If it's even, 5,000 is even. If you subtract 1 and divide by 2, you're going to get an odd node. That's 4,999, which divided by 2 gives you 2,450 plus half of 98 or 99, which is 48. I think they both give you 2,998. No, not 2,000. No, 2,498. 2,498. 2,499. Let me think about that a little bit more. 5,000 minus 1, 4,999. Divide that by 2. The 4,000 becomes 2,000. The 900 becomes 450. The 90 becomes 45. So you get 2,495. And then 9 becomes 4. 2,499. I think it's in both cases. Yeah. So actually, in both cases, you get 2,499 if it's odd, if it's even. If it's odd, let's say it's 5,001, subtract 1 divided by 2, you get 22,500. If you subtract 2 and divide by 2, though, you're going to get not 2,500, you're going to get 2,499 again. So there is a meaningful difference there. I'm not sure which one to expect. Well, for sure, if you divide by 2, if you subtract by this 1 or 2 and divide by 2, you're always going to get a whole integer because that's how these are generated, right? So it's clear then if it's odd, you would do subtract 1, divide by 2. It's even, you subtract 2 and divide by 2. And then you recurse several times until you get to the root node. Yeah. And then so you recurse several times or repeat several times so you get the root node, and then just reverse that process back down. And if you have those nodes all the way through, then your find routine works. If not, then you return false because you'd hit some node where you're not going to get the correct path to the value. I think that's the way to do this. That actually is substantially more complex than I thought it was going to be, but that should work. I think that's correct. But yeah, that's a more complex one, I guess. Let me see the chat is good here. What's up, chat? Hey, Pro Guy, welcome. How's it going, Code Guy? Hope your day's going well. Why don't you teach these topics on your channel? I would love to hear from a smart person. Thank you, man. I appreciate that. Thank you. I should do that. I think that's a good call. Your LeetCode ID. I want to follow you. Subscribe. What's up? Well, welcome, Devkin, and Ansharma. Devkinand Ansharma. I appreciate that. Okay, let me show you. Let me show you. So here's my whoops. Here's my LeetCode. Whoops. Here we are. Yeah, I've solved a few. I have a lot more to go though. Got a lot more to go. But I appreciate it. I appreciate the support. Appreciate that. Yeah, so I think that's going to be the way to solve this one. We'll go to the next one though. I'm not going to code it because I already solved it, but this one I solved too. Okay, I'll explain this one too. Sorting the sentence. A sentence is a list of words that are separated by a single space with no leading or trailing spaces. Each word consists of lowercase and uppercase English letters. A sentence can be shuffled by appending the one indexed word position to each word, then rearranging the words in the sentence. Okay. I have to think about that. For example, this is a sentence can be shuffled as sentence for A3 is to this one, or is to sentence for this one, A3. Okay. Oh, the one index word position to each word and then rearranging the words in the sentence. Okay, so that's the shuffle. Okay, so you append the one indexed position to each word and then you swap them around and permute the words. Okay, got it. Given a shuffled sentence containing no more than 9 words, reconstruct the original sentence. Okay, so the trick here, the key here, is to split each word on the single white space, right? And then figure out the index of that word from the last character, of each of those strings, and then recreate, construct the string with those words in the correct spot. So that's a really interesting. I like this. This is a good question. I like this one. I've solved this one already, so I won't go through it again. But that's the basic premise, basic approach. And I think there's an easy way to do this in C++ using. You can use string find. I want to say to find the space, and then you can use a string substring to get the word that's at that string at that point. And then you could write those into a I think it's at most 9 words. You could write those into a vector of words. Of strings, a vector of strings. You could write each string into the vector of strings. And then also save like an array of integers that at the index of the string, you also have the index of that integer array, which has like where it's going to go, and then you can read both off simultaneously and reconstruct the string by just concatenating. So yeah. Well, or you could. That's maybe not the best way to do it. I want to concatenate at the end, but I would say take the I got it. Sort the array of strings that I've just created, sort it using the array of positions, and then concatenate straight across. That's probably the easiest way to do it. I like that approach. That's probably, yeah, I think it's a little bit easier, because if you make it a little more complex than that, then I think it gets a bit awkward. Yeah, I think that works okay. I was gonna say, actually, you could even do better than that. Instead of creating a second array of integers that keeps track of like what these values are, you can just dump the you can split the strings into these segments as mentioned, and you'll get a vector of strings, and then you can sort that vector of strings itself based off of the last character of each string. That might be a better way of doing it, easier way of doing it. And then when you read off, you just exclude, you just substring each string, excluding the last character, or you just pop the last character when you concatenate. You can, since you're creating this vector of strings anyway, and I guess you could use a string view to make things a little bit easier if in C++ to be a little more optimized. But yeah, that might be a little bit better actually to reproduce this. Yeah, it's a pretty interesting question. I like that one. It's a peculiar one. Basically taking a permutation and reconstructing the original. It's a cool idea. All right, let's go to the next one. Message retract. What's up, ECB? Welcome. Hello. Howdy. All right. Oh, I solved this one too. Find first palindromic string in the array. Given an array of strings words, return the first palindromic string in the array. If there's no such string, return empty string. A string's palindromic if it reads the same forward and backward. Okay, this isn't too hard. A couple of things to say. So this is an array of strings. It's a little bit easier, but if it was just the first palindrome in the string, there's an algorithm for palindromes. It's pretty comes up from time to time with palindromic questions called Moniker's algorithm. So this would be Moniker's algorithm. And when you're dealing with palindromes, it's usually relevant. So efficient method for finding the longest palindromic substring in a given string in linear time, introduced by Gladden K. Moniker in 1975. So they figured this out like 50 years ago. More than 50 years ago. It's been known for over 50 years, which is a pretty long time. But yeah, so there's an explanation, but I'm not gonna explain it. It's an interesting thing. It's basically it's one of those algorithms that it's sort of a sliding window algorithm, I guess, if I had to summarize it. And it doesn't just find all the palindromes in the string. It finds like all of, like, at each index it'll find the size of a palindrome. I think you can design it in a way where it will find like to the right, how many characters to the right of that position are going to match the characters to the left, like how far that goes. sort of like almost like an onion shell kind of a thing, something like that. I don't remember exactly Moniker's algorithm. I don't have it memorized, but I kind of have it sort of I partially remember it. But yeah, that's Moniker's comes up a lot. In this case, though, we don't need monikers. In this case, we just check directly if each string is a palindrome. So the easiest way to do that is if it's an even or odd. Really the easiest way to check if a string is palindromic is exactly what they described here. Just reverse the string and check it against itself. So if the string is equal to itself reversed, then that's probably the most straightforward way to do it. But another way to do it is to just, if it's odd, start the character on the left side, go left to right, and match that against the characters right to left until you've matched all the characters. If it's even, then you would start sort of at the midpoint on the left side and match left to right with right to left. It's slightly more efficient than just copying the string and reversing it and checking it directly. But it's not that much. It's not efficient enough where you would avoid that. Like in an interview, you probably would just do the reversal because it's just way faster to program. But yeah, in this case, it's very straightforward. So I'm not going to program that one because we've already solved it, but that one's on the easier side for sure. Hi, what's up? HG Suresh. Hello, welcome, howdy. Every day's going well. Welcome. I solved this one too. Solved a bunch of these already, huh? Reverse words in a string 3. Given a string S, reverse the order of characters in each word within a sentence while still preserving white space in initial word order. So the way this one works, you would, I think I did this on Python probably. I don't know if I did this in C++. I probably did in Python. Let me see how long ago I solved this. I solved this in 2019 in Python. So actually we'll do the C++ version. So this is basically a, what you do is you split into words. I think you reverse the whole string, split into, it's like a reverse split reversed kind of thing. I'm trying to remember exactly how this works. So, yeah, if you reverse the whole thing, then split, and then reverse each word. No, that'll reverse the word order, not the character order. We want the characters. So this you would split into words, reverse individual words, and then join. Yeah, that works. Let's see. Okay, there's subset single space. So we'll program this in C++. This isn't too bad. This isn't too bad. Oops. All right. So let's try this. Result. I'm gonna say, so we want to do s.find. It's gonna be a single space. That kind of makes things a little bit easier. And we're going to say position. And we're going to say position if so position equals s.find is not equal to, or actually, yeah, it's more like this. Is not equal to stood string end position. And then we say, I want to say we increment the position, something like this. And then we're going to say const, no, not const, it's going to be stood string temp is going to be s dot substring. Come back to that in a moment. We're going to reverse the temp. And then we're going to append the results. Position's gonna start with 0. We're gonna find this next position. I think I have a previous position 0 as well. 0, position 0, previous equals position. And it's gonna be position plus 1, I think. Something like this. I gotta think about this a little bit. So, and then we actually just add at the end here. These might want these to be up here. Just gotta run this one more time, I think, because this is gonna end. Oops. Explain it. I don't know why I gotta do it one more time here. I can do it one more time because this is going to exit when basically it's gonna miss the last word if I'm not careful here. And the substring is gonna be previous to the number of characters, something like this, where it's the previous position, the number of characters is going to be the position of this minus the previous position. So like if you have ABC in a space, it's going to be 0, 1, 2, 3. 3 is the position we get. 3 minus 0 is the number. Yeah, I think it's position minus previous is the substring number of characters. And then we would say plus a space. Same thing here, previous. And this one, we don't get a space. Something like this. There could be some off by 1 errors or something going on here. Let's see. TLE, okay. Not what I would want. Okay. Oh, I know why. Find from position. I think that's part of what I'm missing here. There are a lot of pieces to this. A lot of elements. Let's see, what did I get? Okay. Okay, it's close, but not quite right. Why did it go in the reverse direction? Wouldn't this... Wouldn't this take let's first? Why did it... Wait, what? Temp substring, previous position, temp begin, temp end. Result plus equals temp. Huh. Why did, huh? Wait a second, what? What is going on here? Oh, I must have misunderstood something here. Huh. What am I missing here? Where's my, oh, wait a minute, what? Oh. Huh. Huh. Oh, that's interesting. This debug code isn't running. Huh. Okay. I must have an error somewhere that I don't realize. Okay. Syntactical error somewhere. Okay. S.find position space. Let's look that one up. It might be better to do CP buffer reference. CP reference. Yeah, this might be better. Let's do somewhere here strings. This is I tend to struggle a little bit with string manipulation because it's a bit complex in C++, and I tend to so you guys can see what I'm looking at, and I tend to make very slight mistakes. I think we could argue I just need a little more practice, basically. Where are the? Here we go. That's what I'm looking for. Search. Okay. Oh, wait, no. Where's the find? There we go. Okay. The position comes after. Okay, that might be the issue. Oops. Where's the yeah, position comes after. Okay. Count. Character position count. Number 2. What's that? Find the first substring equal to the range s plus count. This range may contain null characters. If ss plus count is not a valid range, the behavior is undefined. What does that mean? What does that mean? S plus count in the range? First substring equal to the range s plus count. This range may contain null characters. I'm very confused by this. I don't know. Can you give me an example of this one? Character string to search for count length of a substring. Oh, okay. I see. I see. So this just bounds the length of the. Okay, that's interesting. But yeah, I think I've made this mistake before. That must be what's going wrong. That's why the debug's not printing. There we go. Okay, I was so confused. I was like, what did I do wrong here? Yeah, the string manipulation can be a little more complex because of the extra subroutines involved and the syntax. You kind of have to remember the correct syntax. Okay, there we go. So that's how you do that in C++. Also, I didn't really cover how you might do this if there was more than just a single white space. Like if there was more white space than just single spaces, that's a little more complex, but there are ways to do that too. Probably if you had more white space, and just a single space, I think what I'd end up doing is I do something very similar to this find routine, but more likely what I do is I would alternate between searching for things that are not white space as like a chunk of text, and then searching for a chunk of text that is white space, and probably I'd have to think about how exactly I'd want to handle that. But I would likely take the chunk of text that's not white space, reverse it, append it to my result. Take the chunk of text that is white space, not reverse it, append it, and then keep repeating that way. Something like that. But yeah, I would have to alternate each search procedure, toggle the search procedure. So it'd be a little more complicated programming that. The loop conditions would be a little different, I think. I might have like a toggle. Like there's a way to toggle your loop conditions, which is peculiar. But yeah, I've done that before. I've had toggling for loop conditions. It's definitely a very peculiar thing, but you can do it. I've done it before. All right, let's see what else here. Maybe keep this open in case I do more string stuff. I need to actually charge my computer. Let me check the stream health, and then maybe I'll charge the computer. It's been like an hour, which is good. Stream is healthy. Let's grab another question, and then I'm gonna go ahead and grab another question, and then go ahead and plug in my computer while I'm thinking about this question. Sum of all odd length subarrays, given array of positive integers array, return the sum of all possible odd length. There's my subarrays of array. Interesting. The odd length subarrays. Well, that's peculiar. Can you do this in linear? Yeah, I was gonna say there's probably is a way to do this in linear time. Gulp. So the sum of all subarrays can be done pretty efficiently, I think, by excuse me. Think about the sum of every subarray. The sum of every subarray would be like adding each. So the subarrays of size 1, you'd add each element once. Subarrays of size 2, you'd add each element twice, except the first and last element. I think that's correct, because there would be overlap. Subarrays of size 3 would be every element once, twice, 3 times across, then twice and once again is the pattern. And then if you add these things all together, you have 1s across, 1, 2s across, 1 across, 2 across, 1, 2, 3 across, 3, 2, 1. You add them all up, you end up with like 3 plus 1 plus 2 plus 3. 1 plus 1 plus 1, 1 plus 2 plus 3. Or, yeah, 1 plus 1 plus 1, 1 plus 2 plus 2, 1 plus 2 plus 3. Interesting. So like each element would end up being added. Like you could calculate that, I think. You could figure that out. How many times does each individual element get added if you added all the subarrays, sums of all the subarrays together. Excuse me, I think it's going to be for the first element and the last element, it's just the size of the array, n times 1, I think. Well, let's say if it's a size 4, you would do 1, size 1, size 2, size 3, and size 4. Yeah, before the n. N times the first element. Then the second element is n minus 1 times 2 plus 1. Then next element's n minus 2 times 3 plus 2 times plus 1. And so it's going to be n minus I times the index times x. Or yeah, n minus I times the index plus the sum from 1 to I. From 1 to I, which is going to be, I think, I times I plus 1 over 2. And then that whole quantity. So n minus I times I plus I times I plus 1 over 2, that whole thing times the element. You take that over the sum over all the elements. I think that's the solution for just the sum of all the subarrays, and then the sum of all the odd length subarrays. Basically, you're going to cut that down. Somewhere in there you modify those values. So I think the I times I plus 1 over 2 term probably becomes more like I squared, because you're just not adding the even values in between. Probably something like I squared maybe over 2. Excuse me, I have to think about that a little bit more. And then for the even values, not the even values, for the other portion, where it like gets capped, I guess. I think you just divide by 2. So instead of being n minus I times I, it's like n minus I times I divided by 2. It's something like that. But yeah, I'm pretty sure this can be done in linear time. Just need a little bit of, I guess, manipulation. All right, let me go ahead and plug my computer in, and then I'll come back. 1 second. Okay. All right. Let's give it 1 second here. All right, we're back. So, let's try to do it in linear time. So as I mentioned, let's say it's going to be something like the following. I want to say, this is a good question. Actually, let's do it this way. The number of times this particular element gets added. All right. If the array is of length 1, 2, 3, 4, 5, we're adding 1 once for the size 1, 1 once for size 3, and 1 once for size 5. So 5, 3, and 1. It's 3 times. So it'd be like 5 minus 1 divided by 2 plus 1. I'm going to use n. hopefully simplify things a bit. Whereas if it was just I is 0, right? The first element, it would be n minus I is 5. But in this case, it's half of that plus 1. If it was even, so 6. So I think yeah, you subtract 1 divided by 2 and add 1. I'm not sure. If it's 6, you would do 1, 3, and 5 again. It'd still just be divided by 2. So if it's even, you divide by 2. If it's odd, you divide by 2 and add 1. Interesting. And just think about that for a minute. Do you add 1? There we go. Add 1 first, and then divide by 2. That's easier. Okay. Add 1 first, then divide by 2. So 5 becomes 6, divide by 2, you get 3. 6 becomes 7, divide by 2 is still 3. Okay. All right. Now, how is that related to I, however? Well, let's say we shift over to I is 1. How many times does 4 show up in the odd length subarrays? Oh yeah, this was 1, 3, and 5, right? So this one's going to be also 1, 3, and 5, but it shows up twice in the 3 and twice in the 5. Yeah. Let's do it like this. Let's do it's like the first count and the second count. They're like two parts to this. This is going to be the like flat count, and this is going to be the rising count. I'm not really sure what to call those two things, so I'll call them these things. I'll call them this. So this expression minus I. Okay. That may or may not be correct. I'm not sure about this. This might be a minus I here or something. I'm not sure where this minus I fits in. I think about it. So for 4, I plus 2 is correct. It's twice. 1, 3, and yeah. In each of the subarray lengths that are 3 and 5 and so on, the ones that are greater than or equal to 2, it's going to show up twice in each of those. It shows up in the 3 length, 3 once, twice. It shows up in the 5 length once. There's a rising, there's a falling, and a flat amount. if it were not odd length, it would be once for 1, twice for 2, 3 times for 3. Well, not 3 times for 3. Like the 2 is 3 times for 3. But 4 is not 3 times for 3. Oh, that's confusing, huh? Hmm. Once for 1, twice for 2, twice for 3, and only once, I think twice for 4, and only once for 5. Okay. The reason why it's only twice is because it's going to be the minimum. It's because it's like locked on the side. I'm not sure how to express that. It's because it's too close to the side. So even though you have these larger arrays, they aren't going to reach this number more than 2 ways. Oh boy. Oh, so actually, this flat part is a little more complex than I thought initially. It would actually be you'd actually subtract 2 of each I value, so it would only appear 3 times as 4 times 2. I think this is doubled. That's what I'm saying. That's if you just added all of the subarrays, but if you just added the odd length subarrays, I think it'd be 3. I think if I took n minus I, let's do it like this. The amount's going to be 2 for sure. But in this case, it would also be a 2. Like for 5, 5 and 4 mirror each other. Constant. I'm not sure what to call this. Like, let's just say bound. It's going to be the smaller of these, I plus 1 and n minus I. So if I is 1, it's going to be the bound between, it's going to be either bounded by 2, but if also I is 0, 1, 2, 3, there's going to be n minus I, which is 5. Basically the indices on the other side. So 1 and 1, 0, 1, 2, 3, 4. The smaller of these two. So 1 and 4 plus 1. And then when you see 4, it's going to be 1 plus 1 is 2. So it's going to be this bound. And then so the flap count is going to be multiplied by this bound. And then also, that bound, I guess, defines how many of these other values are not included for that bound. So like at I equals 1, we're going to have these 3. At I equals 2, it's just this middle element. And the other ones are going to be sort of rising values. So let me think about this. It's not I plus 1. By the way, it's this bound. But what I'm multiplying by the bound is, I want to say n minus bound. Again, this is for if it's not odd length. Odd length is a little more complex, but let's just suppose it was not odd length. In this case, it would be, 5 minus 2 is 3 of these. And then when I is 2, 5 minus 3, that's not quite correct, because this basically doubles at each iteration what's being removed. The correct way to understand that would be like, it would be sort of like bound minus 1 bit shifted to the right. This, I think, is the correct flat count for non-odd length. So for I is 0, the whole thing's a flat count, which gives you bound is 1, n minus 0 times 1 is n. So that's what you would get for the first element. The number of times that shows up is 5 times, which is correct. The rising count would be 0 there. For I is 1, we get this bound of 2. 2 times 2 minus 1 is 1, bit shift to the left is 2. So we would get 1, 2 of these excluded, 3 times 4. 3 times you would get 2, which is correct. It's going to be the 1 case, the 2 case, we get 2. The 1 case it's excluded. The 2 case, the 3 case does this twice. The 4th case does this twice. And the 5th case also gets excluded. So I think that's correct for the flat count. And then the rising count is going to be, we're going to do it's basically n. So whatever the bound is, just call it a temp variable. This might be easier. So this rising count is a little bit more complex. It's going to be the sum. So like if you're looking at 2, it would be 1 plus 2, and then this one has a 3. And it's 1 plus 2 on the other side too. So you'd multiply by 2, which is, I already have that here. This rising count times 2. This 1 plus 2 comes from, I think we said the bound was 2. So actually, I think Yeah. So here the bound will be 3. And we're gonna have the sum from 1 to 2, not up to 3. So we subtract 1 to 2. So it's gonna be the sum from 1 to 2. Sum from 1 to 2 is gonna be that value times itself plus 1 divided by 2. So 2 times 3 divided by 2 is 3. Yeah, so this works for the sum of all the subarrays. But for the odd length ones, things get more complex. So those of you who have been following me so far through this, I appreciate that. This is definitely one of the more complicated. If I just run this, I won't get the right answer, but I'll get I can at least verify that my thinking is correct here. So I got 110 for this one. So we get this sum 5, 6, 7, 12, 15. I don't know if I want to do all of that by hand. That might take too long. Let me not try to verify that all by hand. It'll take a while. The next thing is, all right, how do I modify this for the odd counts? With the odd length arrays. I wonder if I just divide by 2. That'd be kind of funny if it was that simple. It almost looks like that. No, it's not. Okay, I was gonna say if I could just divide by 2, it'd be nice. It's close though. Let's see, did it work in this case? 110. Add these 3, add these 2, add these 2, and then add each 3 again. So that would be 21 plus 12 is 33. 33 twice is 66. And then add 76 plus 12 is 88. And then plus 22. Yeah, I did get that. Did calculate that correctly. Let's see about, okay, in the odd case now, how does this change? Well, the flat count is going to be, let's think about this again. So we're still going to do, like, let's say in the second case, it's still going to be a 1, but we're not going to have the 2 in there for the rising count. So the rising count is still going to count 1, but we're not going to have, it's not going to, no, I'm sorry, let's do the case, let's do the middle one. Let's do 3. It's a little bit easier to think about 3. So for the rising count, it's going to appear once in 1, and it appears once in 3. So we do still get 1 plus 2 there. Actually, no, maybe it's better to try 4. I feel like I need more elements to really understand this. That's confusing. That's very confusing. It's very confusing. Let's do 4 and then 2. Let's just do them separately and see where it goes. So, in this case, we do add one time for the 1 case, and we don't add 2 for the 2 case, and we don't add 2 for the 3 case either. We do add 2 for the 3 case though. Do we add, and we add 1 for the 5 case, so it becomes 1 2 1 instead of 1 2 2 2 2 1 2 2 2 1. It becomes 1 2 1. Okay, so we lost 2 elements for the flat count, basically. This section, this part, basically was divided by 2. Instead of 3 multiplying by 3, we multiply by 1. And I think that's basically it, actually. It's just, you just take this whole thing, add 1, and divide by 2. I think that's it. So save flat count modifier. Yeah. I can just add one and divide by 2. Right, because it went from 3 down to 1. Actually, no, I don't think you even add 1. I think you just straight up divide by 2. Yeah, 3 would go down to 1. What is 4? 4 probably goes down to 2. This doesn't have a 4. Yeah, it doesn't have a 4. If you had a 6th element here, then it would be at 4 here for the parts that would be counted twice. It'd be 4 times. In that case, what did I say? I was saying that it would only be twice. So if there were 6 elements, you'd do 2 times would show up twice. 3, no, yeah, but that gets discounted. 3 times shows up twice. 4 times gets discounted. 5 times shows up twice. No, 5 times would only, yeah, 5 times would show up twice. It wouldn't show up once now, it would show up twice. And then 6 times would get discounted. So you'd have 1, 2, 2. You would, yeah, it's divided by 2. Okay. It seems a bit odd, but yeah, flat count modifier, just divide by 2. And then that's for the odd case, and then the rising count is, it's still going to be, like for 5, it's 2 times 1. But this is a different formula here now. So what happens now is, like, in this case, it's still just 1, right? Because you just have 1 and 2, 2 to 2, 1, 2 to 2, 1. But when it's the odd length subarrays, it's 1, 3, 5. So this is going to appear in 1 and in 5 still. So that actually doesn't change in that case. We'll come back to that. But in this case, it would have been 1, 2, and 1, 2. But instead of being 1, 2, so the multiply by 2, I think on both sides is still correct. But getting 1 plus 2 here, I think, is incorrect now, because that would be for the 1 case, the 5 case, or the 1 case and the 2 case. And the 3 case is where it's the 3. 1 case and the 2 case, but the 2 case is gone now. That's what I'm saying. So yeah, it's just the odd version now. I think it's just temp squared. It might be this. I'm a little confused by this part. That's confusing. So the bound was 3. We said we're going to add from 1 to 2, but we're going to exclude 2. And it's going to be the sum of odd values. Huh. Yeah, if we did the sum of the odd values, like where 2 is the index of the odd values, so like 1 plus 3, then it would be 2 squared, which is 4. But it's not that. It's the odd values that are bounded by this index. So like the odd values less than 2, for example, or less than or equal to 2, which is a little bit more complex. The odd value, the number of odd values that are less than or equal to some number, let's say x, it's going to be, I think, just divide by x. So just say temp modifier. So this is going to be squared. But this is going to be the number of odd values less than or equal to a certain, less than or equal to temp, which is going to be like 1 to 2 is just one value. So you could divide by 2, and that gives you that. 3 values though, so you would add 1 divided by 2. It's a lot involved here. There's a lot of things going on here. This is pretty messy. I think you add 1 divided by 2 and then square that. So, yeah. So for 2, you add 1 to get to 3, divide by 2 gets you back down to 1, and then square 1 times 1 is 1. For 4, add 1 divided by 2 gets you down to 2, and then square 2. So 1 plus 3 gives you 4. Yeah, okay, I think that's right. Is this correct? I don't know. I guess we'll find out. It might be just as it is. No. Okay. It's a rough one, huh? How's Chad doing? What's up, Chad? They're probably like, you're on your own for this one, bud. This is definitely a more challenging approach. There's probably a much simpler way to do this, but this is one way of doing it. I'm very tempted to use like sliding window or something, or like a prefix subarray or something that just makes this a lot easier rather than trying to directly compute how many ways each element gets added. Although it can be done, I think. I'm sure there's a much better way to do this. It's a lot faster. A lot simpler. Excuse me. I might be spending too much time on this, quite frankly. Hmm. All right. So I missed something here. On the first one, I have this temp modifier here, temp modified, and this rising count. Apparently this is off by 10. How many times does 1 get added? Let me debug this here. No. I might want to put this on. Actually, do it this way. Okay. Let's see what numbers I get here. For this 14253 case, I should get. So this is the total, the number of times. So this appears 1, 3, and 5, and one time each. It should be 3, not 1, not 2. This is off by 1. This appears once in the 1 case, twice in the 3 case, and once in the 5 case. So 1, 2, 1. Yeah, that's correct. So this is right. The second one, this 2, should appear once in the 1 case, 3 times in the 3 case, and then once in the 5 case. So this should be a 1, 3, 1. This should be 5. So this should be 3. This should be 5. This should be once in the 1 case, twice in the 3 case, once in the 1 case, and then the last one. Yeah, so this should be 3, 4, 5, 3. Wonder if it's that simple. Um, 3, 4, 5, 4, 3. Oops. Whoa. Try to think about this here. 0, 1, 2, 1, 0. I gotta invert that. If I did n minus, it'd be 5, 4, 3, 4, 5. I'll do it the other way around. If I added this, I would get 5, 6, 7, and then I just need to subtract. 5, 6, 7, 6, 5 minus 2. Okay, it's wrong, but it's close. It's close. It's not correct. Okay. It might be as simple as this. Oh, no. Let me see, in the 3 case, it should be 10 gets added once. And once in, yeah, there's 1, 2, 3, there's 3 times. It's 1 for 1. No, twice. 1 for 1, 1 for 3. It's twice. Um, 11 is 1 for 1, twice for 2, 1 for 3. So it's 2, 4, and 2, I think. Okay. No. No, it's 2, 2, and 2. It's 2 all the way across. Each one gets added once for, yeah, it's just twice all the way across. So this is wrong. um, yeah, this is wrong. Okay. It's a fun idea, but it's not correct. A little bit more complicated than that. All right, let's go back to what I was doing then. Oh man, this is involved, huh? Let's see. So I said it should be 3, 4, 5. And rather, I'm getting 2, 4, 2 again twice. This one's a little bit easier though. I think this is just 1, 1. Yeah. And this one should be 2, 2 across the board. Instead of getting 1, 2, 1, I should just be getting 2, 2, 2. Okay. So that means this should be slightly higher in these cases. Okay. All right. The so the flat count for the first case should be I think it's going to be 1, 1, 1 all the way across, right? 1, 0, 1, 0, 1, something like that. And then the rising count is just 0. So I say the bound for I equals 0 is 1, temp is 0. Yeah, so this rising count doesn't count at all for the first one. But the flat count is it's 5 minus this temp, which we said is 0. So 5, so it'd be 2. Flat count modifier is 2, which is not correct. I think it should be a +1. Oops. Uh-oh. Uh-oh. Stream's still live. Let's see. Just give it a moment. Uh-oh. Uh-oh. Okay. Yeah. I think that gets a +1 there. That might be part of the issue there. Oops. Okay, there we go. A little bit better. So now this is correct, but this one's not correct now. So this should be a 4, not a 6. Let me think. How does it handle? So it handles for, it says n minus 10 plus 1. So this bound will be basically 1. Temp will be 0. N minus 0 plus 1 divided by 2 is 3. Yeah, that's correct. 1, 3, and 5 gives you 3 different odd values. If we're even at 6, you would get still get 3, which is correct. Okay. That's the correct flat count modifier for I equals 0 case. But when I equals 2, now you're doing 1, 3, and 5. But in this case, 3 is the only one that you would consider. Which is where this temp subtraction comes from. So now n is basically like 6. And what do we subtract here? This temp part. The bound, I think we said is 2. I is 1, it's 2. Subtract 1 is 1. Multiply by 2 is twice. Oh, that's confusing, huh? Oh. Yeah, it is confusing. Oh my gosh. Oh, oh boy. This is getting complicated. Let me maybe let's start over, but remove some of this. Let's just remove some of this. Kind of try to think about this a little bit differently. I'd start over, but maybe take a fresh look at it. Excuse me. All right. Let's try this again. So, how many times is this going to show up in the odd cases? Well, it shows up once for 1, once for 3, once for 5. In fact, when I equals 0 and when I equals 5 towards the edges. So we do want this. This is going to be sort of near edge, or I'm not sure what to call this. We'll call this edge distance. Or distance. That'll be the index, and then sort of reversed as well. So 0, 1, 2, and then 2, 1, 0. There's some symmetry here. You could even call it like symmetric index, something like that. Symdex. All right. Now, with our symmetric index, what I want to do is count the number of odd times the I plus 1. So we're going to say flat. I guess the flat part of this calculation. That's how many times we multiply by I plus 1. Which is going to be sim index plus 1. Not I plus 1, the sim index plus 1. Okay. Now the sim index plus 1, I think that's one of the things that changes here. In the odd case, 0, you get I plus 1. At I equals 1, you get it should be 2, right? 3 and 3. In this case, it's still 3 because of the 3 amount reaches us 3 times. But 1 and 5 only reach once, so it is still sim index plus 1 for the flat part. And the number of times it occurs is going to be, I guess it's going to be basically the number of times the odd sized subarrays are going to be larger than the sim index. Oh, really, the number of times the sim index is larger than I'm not sure how to express that actually. So the number of times there's a lot of symmetry involved here. It gets confusing. The number of times the odd length subarrays not only exceed the sim index value, because they have to, but also those arrays themselves modified should exceed the sim index. So, for example, like 4 and 5 should actually just count as 2 and 1 again, which is confusing. So the symmetric version, or the reflected version, I'm not sure how to express that. It's like uh it's not 4 and 5 compared to the sim index. It's 1 and 2 compared to the sim index. And it should be exceeding greater than or equal to the sim index plus 1. That's the flat number. The number of times that those lengths are greater than or equal to sim index plus 1. And those lengths are going to be, you could just extend it up to the midpoint and then multiply by 2. But yeah, those lengths that it's going to be, in this case, it's going to be 1, 3, 1 for the odd ones, right? Because we exclude 2 and 2. So the numbers we're dealing with are 1, 2, 3, 2, 1. The number of times those numbers exceed greater than or equal to 3. Yeah, that's really confusing. I don't even know how to explain that in English, articulate that. Yeah, they're like symmetric versions of themselves, something like that. Yes, so calculating this flat portion definitely is not obvious. It's not that hard, but it's definitely not obvious. So the number of times that array of elements, let's say, is greater than or equal to sim index plus 1, I think can be calculated in a formulaic way, but it's just not obvious how to do it. Not immediately obvious. Like I said, in this case, it's going to be 1, 2, 3, 2, 1. It's going to be the elements. And the sim index IDs, sim index plus 1 values are also going to be 1, 2, 3, 2, 1. So obviously the first time the number of times exceed 1. Oh, and we don't include the even value. So it's 1, 3, 1 rather than 1, 2, 3, 2, 1. It's going to be 1, 3, 1. So the number of times we exceed 1 is 3 times. Number of number of times we exceed 1 is 3 times. Number of times we exceed 2 is once. Number of times we exceed or greater than or equal to 3 is once. And the number, or not exceed, but greater than or equal to 1 is 3 times, 1 time for 2, 1 time for 3, 1 time for 2 again, and then 3 times for 1 again. So it becomes 3, 1, 1, 1, 3 is this flat amount, which I think is correct, by the way. Yeah, that's really confusing. That is really confusing. How can I encode that? How can I compute this? 1, 2, 3, 2, 1. So if it's an odd number that we're dealing with, let's suppose we remove it for the sake of argument, because I can say we're just going to double the number of times. So we can split this into 2 components. It's a flat, even, and then odd portion. Odd portion. If it's even, we can just double this part, which is going to be the number of odd numbers that are less than or equal to, it'd be sort of like n minus 1 or something. And what did I say? It's going to be, so if with 5, the largest number you get is 3, which is n plus 1 divided by 2. That's the largest value you get. Hold on, computer is struggling here. But actually, that's not the part that we're going to double. We're actually going to subtract 1, I think, and divide by 2 instead. If it's odd, that's if it's odd. If it's even, we don't need to subtract 1. Yeah, 4, the largest value is 2. Yeah, if it was 4, it'd be 1, 2, 2, 1. Which is symmetric, right? So I think we only subtract 1 if it's odd. And I don't think you need to subtract 1 if it's odd, by the way, because this will automatically, when you bit shift, it'll remove that. Doesn't matter. Okay. So now that gives me the upper bound on the number of odd numbers. Oh, this is peculiar, huh? Look at this. Look at that, man. Oh my gosh. Oh, you gotta be kidding me. Ooh. Okay. So it's the number of odd numbers. How's stream doing, by the way? Okay. So here you would have 5 divided by 2 gives you 2. And then I'm saying square that and bit shift to the left. I don't think that's right, by the way. 5 divided by 2 is 2. Hold on. I'm sorry, it's really hard to focus. Give me 1 second. Oh, there we go. This is so confusing. I'm sorry, I'm also like distracted a little bit too. All right. This isn't the right one so far. Let me just. You've got this symmetry, right? We're going to remove the odd part. So we consider the largest value you can go up to is going to be 2 for 5. So yeah, and n divided by n bit shifted to the right by 1 is probably fine. And then what happens is we want the number of odd numbers that are less than or equal to this value, 2. The number of odd numbers that are less than or equal to that value. So let's just do constant odd helper. Is not so simple. That's going to be, I think, add 1 and bit shift by 2 again. So the number of odd numbers that are less than or equal to 2, I think it's just 1, right? So you add 1 to 3 divided by 2, you get 1. About 3. Yeah. So that, and then this odd helper squared. This is the number of, and then you bit shift that by 2. Oh yeah, that's really confusing. It's kind of ridiculous. So yeah. Oh my gosh, man. Oh my goodness. Oh. Okay. I didn't choose the LeetCode life. The LeetCode life chose me. uh, I think that's correct. That's so messy, but I think it's correct. It's also make sure I have the right number of. All right. So we're gonna just consider the odd portion. So 5 divided by 2 is 2. Counting the number of odd numbers that are less than or equal to 2, we're going to add 1 and divide by 2. And then you can square that number to get the sum of all those odd numbers. Okay. And then this is the even part. And this is we'll call this even helper, actually. And then what's going to happen is we multiply that by 2 because it's on both sides, right? From left to right and right to left. We're adding that together. That yields the flat even portion. The flat odd portion I'm sure there's a way to optimize this, by the way. Somehow my computer started to struggle with this. Um, the flat odd portion, I think, is a lot simpler. It's just going to be basically this n divided by 2 is greater than or equal to sim index plus 1. I think it's like this. So if it's 5 divided 5 becomes 6 divided by 2 is 3. 6 would still be 3. 6 plus 1 divided by 2 would be 3. Yeah. This is, yeah, 6 would be 0, 1, 2, 3. Yeah, it's just the sim index portion. So yeah, it's gonna be n and 1. So this flat odd portion is just a check if it's an odd sized array. Then we're gonna check if that point that we've removed exceeds the sim index or not. So sometimes we add this extra part and sometimes we don't. Okay. So that's the flat portion. Yeah. Okay. Now the rising portion. All right. This is not going to be the sim index plus 1. This rising portion is a little more complex. It's 0 in this case. There's nothing rising there. In this case, it should be a 1. And it should be a 1 on both sides. The 3 count has the sim index number. The 5 count only has a 1. That's part of the rising portion. So you multiply the rising portion by 2. And yeah, my computer is struggling now. I don't know why, but it is struggling. Now, how would I compute this? It's very similar to what we just computed, the flat count. But it's a little different. It's more like this flat even portion. I wonder if that's correct. I wonder if it's just this flat even portion. That might be the same thing. I don't know. That's confusing. Let's make this just without the multiplier there. Oh yeah, I don't know what's going on, but the browser is definitely having a really hard time. The computer's having a hard time. It might just be, could be a few things. I suspect this rising count is basically the same as this flat even portion. It's the same thing. That's actually what I'm trying to calculate here. By definition, I won't have the flat odd portion. I think it's just the same thing. What happens if I do this? I think it's the same thing. I could be wrong, but okay, compiler. Uh-oh. Wrong answer. Okay. 5, 8, 11, 8, 5. Oh no. That's much too large. Okay. Uh-oh. Oops. Oh man, this is gonna be rough, huh? Yeah, have to keep that in mind for the future. Sometimes the computer struggles. Just it's lagging. So flat count, I got 3, which is correct. Rising count should be 0. Flat count is 6. This is wrong. Flat count should be 1. Okay, flat count's incorrectly computed as well as the rising count. Both of those are wrong. Okay. Let's go back. Just make sure the flat count's right. So that's supposed to be 1. Oh no. Oh, I'm gonna have to cut the stream early. If the computer is, if it's gonna keep doing that, that's gonna be kind of an issue. Or like basically like buffers on my end. Where is that? Why don't you use DP programming? What's up? Tahabuhan. Howdy. It's not a bad idea to try to use DP here. There's a couple reasons not to use DP. So one reason is that I think this can be done in linear time with constant memory. If you use DP for this, then you use extra memory. So I think there is a better solution that doesn't involve DP. That's the first reason. The second reason is that I don't see the DP solution immediately. I have to think about it. The DP solution might be a lot faster to program. Like if you had like time bounds, then I would say using the DP solution in that case is probably best. But the reason I'm not doing it in simple terms is that I think there's a way to do this that's more direct. It's just not obvious. And I'm struggling to kind of formulate it correctly. All right, so the flat count at 6 at 2, yeah, at 4 should be 6. So this was incorrect. So I had 5, this even helper, 5 divided by 2 is 2, plus 1 is 3, divided by 2 is 1. So my even helper should be 1, and then the flat even portion, I get 1 times 1, bit shifted by 2 is 2. And then I get this flat part is 2 plus something else. So this is wrong. This should be a 1. Yeah, this is not quite right. It's even helper is wrong. I'm also kind of surprised because this. Oh, right. Yeah. So this is. I want to say this is more like sim index or something. That might be what it's supposed to be. And yeah, the lag is getting pretty intense. I think it has to do with, I might have to just refresh LeetCode or something. Oh man, this is super awkward. No, that's not the, I don't know what was I thinking before this flat count. This is wrong. It's definitely wrong. It's supposed to be 3 1 1 3 for the flat amount. The flat count, and then the flat count is then multiplied by the sim index plus 1. Yeah, this is wrong. This is very wrong. Let me think about this for a minute. Oh man. What did I do wrong there? It's the number of odd length subarrays that when, I guess, reflected, meaning you take the length and you take n minus the length plus minus 1, I think. So like 1, 3, and 5 becomes 1, 3, and 1. It should be. So it would be, I think it's n minus I plus 1. 5 minus 5 plus 1. 2 would be, no, it's n minus I minus 1. No. I think it's n minus I. It should be 1, 2, 3, 2, 1. So 1 should be 1. That's the minimum of those two things. So a minimum of I and n minus I plus 1. Or n minus I minus 1. So if I is 1, you get 5 minus 1 minus 1 is 3. You should get 1. When I is 2, 5 minus 2 minus 1 is 2. Which should be correct as 2. And then 3, 5 minus 3 minus 1. No, that gives you 1 again. That should be 3. I think it might be plus 1. N minus I plus 1. 5 minus 3 is 2 plus 1 is 3. Yeah, and then 5 minus 4 plus 1 is 2. 5 minus 5 plus 1 is 1. Yeah, take the minimum. So it's going to be the minimum of I and n minus I plus 1. That's like the reflection that's happening. And then where I is the length of the subarray. And then we're going to count the number of those reflected subarrays that are odd, and have a length that's reflected length. I'm not sure what the right word is for that. Like, I'm calling it reflected, but I'm not sure what the right phrase is. That's less than or equal to the sim index plus 1. Or excuse me, is greater than or equal to sim index plus 1. Interesting. Okay. Hmm. All right. Let's try this again. Depending on what the sim index is, and depending on what n is, it doesn't really matter as much what n is. It matters more what the sim index is. It's very confusing. How many of those values are greater than or equal to the sim index? And then I'm going to double that, so that makes things more confusing too. Oh, I'm making this so much more complicated than it needs to be, I think. Probably. Um, Gotta think about it. Gotta sit and think about it for a while. I think I could just use the sim index plus 1 and then count the number of arrays that are greater than or equal to right. Well, the thing that makes that confusing is that the arrays themselves also have that kind of symmetric property, which is why it's this complex, or more complex. Let's just remove the odd part so that way we can just double it. Yeah, okay. That's what I did before. I said we're gonna remove the odd part altogether and compute the even portion, which is just gonna be a doubling of it's basically just like the sim index with some modifications. Excuse me. So also, yeah, this is definitely. I think I gotta refresh the page or something. Let me try that. Let me try refreshing this, see what happens. Hopefully that fixes whatever's going on here. It's starting to like really lag for some reason. I'm not sure what the lag is from. Yeah, it's not good. I might need to. I think I'm okay. I think I might want to restart the stream because this is my browser starting to crash here. Yeah, this is a bit awkward. Okay. Sorry, folks. I might just need to restart. Yeah, this is really something's not right. All right, let me try to solve this question and then I think I'm gonna restart afterwards because this is not quite this is going much slower than it should. All right. So yeah, my thinking here is that I've got to count for that sim index plus one, which for 5 is going to be 1, 2, 3, 2, 1. I've got to count the number of odd lengthed subarrays that are greater than or equal to that particular sim index plus one, and the number of those arrays, and it's not just the odd length arrays, but this odd length arrays modified so that they would be, instead of 1, 2, 3, 4, 5, it would be 1, 2, 3, 2, 1, and then if it's only the odd ones, it's going to be 1, 3, and 1. So I've got to count in that way, which is a little bit more complicated. So the way I decided to do this is exclude the sim index 1 plus 1 value that's going to be odd and count that separately, or the array value that's going to be odd. Which actually the sim index mirrors the array values, so it's really only if I is in the middle of the array. Quite frankly, it's the only time where this really gets complicated is when I is in the middle of the array. So we're just going to say if I equals like if n and 1 and I equals array size, or n divided by 1. Just have to be careful because of this. Then we're going to do something different. But all other cases, I think I don't need to be that careful. Okay. So in these cases, I actually don't need to care about that middle portion at all. And so I can just say, get the sim index, add 1 to it, or sim value, we'll call it. So I don't really even need the sim index value, or sim index itself. It's a symmetric value. And then I'm going to count the number of odd numbers there are, which is going to be something like this. Number of odd numbers that are less than or equal to that sim value. So if the sim value is 2, the number of odd values that are less than or equal to, oh yeah, no, yeah, 1, that's right. The number of odd values that are less than or equal to 2, it's going to be 2 plus 1 divided by 2 is 1. And the number of odd values that are less than or equal to 3, 3 plus 1 divided by 2 is 2. Which is right, you get 1 and 3, yeah. And then the even helper squared. And then we double it as well to get the portion. And then the flat odd portion we don't even need. Don't need that unless it's the oops. The flat count I could put down here. All right. Oh, excuse me. I forgot. Okay, my mistake. Yeah, I'm just gonna like to do. Come back to that. I think this flat even portion is correct. We'll come back to the rising count later. And the flat count. Yeah. This should be something like this. It's a bit confusing. What do I get for semi-mix? Okay. Um, this is maybe a lot more time than is required for this question, but it is meaningful here. I'm not going to commute these other parts here for now. We'll just leave this as it is. I'm just interested in the flat part for now. Okay, I got 32. All right. Should not be 32. Hmm. This should be initially 1. Oh, that's fine. Try that. Okay, 2. It really should be 3, the flat part. It should be 3 initially. Um, oh, I do have to add the odd portion, don't I? It's so confusing. It's very confusing. Yeah, the I do need to add the odd portion. The reason the odd portion needs to be there is because this is the number of oh, it's the number of odd subarray lengths that are slightly modified so that way they reflect um like 1 2 3 2 1 rather than 1 2 3 4 5. that are greater than or equal to the sim value at that particular index. So the reason I still need this flat odd portion, regardless of whether or not we're looking at the middle point, is because I need to add that 3 that's being counted. That's pretty annoying. That's really annoying. No. Alright. Yeah. Okay. Yeah, that 3 is always going to be greater than or equal to the... This odd portion will always be there. It's always going to be greater than or equal to the sim val. So really, this is just whether or not it's odd, quite frankly. Not assert, but cast. That's really annoying. That's really annoying. Yeah, that's just always going to be there, I think. There's no way around that. Okay, let's try again. Gosh, man. Flat is 3. Okay, got it. But these other ones, flat should be 1 across the board. So it should be 3, 1, 1, 1, 1. That's annoying. 3, 3, 9, 3. What is this? This is wrong as well. So it's not the number of odd values that are less than or equal to sim value. It's the number of odd values that are greater than or equal to the sim value. So it should be getting smaller, not larger. That's the other mistake. Oh, that's confusing, right? Yep, very much so. Indeed. Okay. How do I calculate how many odd values are greater than or equal? Greater than or equal? I could subtract. Could do it that way. So we're not going to multiply by 2. This flat even portion is going to be multiplied by 2. The even helper, it's going to be... So this is the number of odd values that are less than or equal to sim value. We want the number of odd numbers that are less than or equal to n minus the number of odd values that are less than or equal to the sim value. And that gives me the number of odd numbers that are greater than the sim value. But we want greater than or equal, not just greater. And we also want, if n is odd, then we don't want to count the larger value for n. So like if n is 5, we don't want to count 3 in there, we want to count just 2. Odd values less than less than or equal to 2 rather than less than or equal to 3 for reasons mentioned previously. Very confusing, I know. Very involved. I'm gonna charge my computer again. Give me a minute. So, yeah. This also gives me values that are greater than the symbol, not greater than or equal to the symbol. So I should actually subtract here. Subtract one instead of add one. Okay, that's a little more what I'm looking for. Complicated. Complicated. Flat count is 5. That would get better. It should be 1, 1, 1, 5, 1, 1, 1, 5. It's much closer. It should be 3, 1, 1, 1. But that is much better. Maybe this is right then, actually. Maybe it's a +1. No. No. There's something slightly wrong here. Okay, I know what's wrong. I know what's wrong. All right. Okay. It's going to be this minus this. Something like that. Although with some slight variations, I think. No. 9? No, it's too big. Then maybe this is +1. I don't think this, I have to think this through a little bit more. Oh boy. Oh boy. No. All right. So it's a tough one. Okay, let's try again. We're gonna say const int odd count 1. Odd sum 1. Odd count 2. Odd sum 2. And then this even helper is the difference between these two. Odd count 1 minus odd count 2. It's, yeah, odd sum 1, odd sum 2. Now, as I mentioned, the idea is that you've got a certain number of elements that you want to know how you want to count the number of those elements that are greater than or equal. And these are odd. And actually, I don't need the sum of these. That's a mistake. That might be what I'm doing wrong here. Excuse me. That might be a mistake. I think I just need the count. That might be one of the errors. Yeah, I just need to count how many there are. I don't need to know the sum of those. Okay, a little bit closer. Three. It should be 3 1 1 1 3, not 3 3 1 3 3. Um. So in this case, 5 divided by 2 is 2. And then sim val of 1. Uh, 2 divided by 2 is 1. This should be 2 minus 1 is 1. So even helper is 1. Multiply by 2. This is odd. Add 1. So it calculates it correctly for the first one. The second value, same thing again, it's 2. Sim val is 2. Becomes 1. 2 minus 1 is 1. I'm supposed to get 0 for this one. Or 1. 0 for the flat even portion. This is a tough one, huh? This is wrong. This is not supposed to be 2. It's odd count 1. I don't think it's odd count that 1's ever supposed to be 2. It's supposed to be 1 3 5 becomes 1 3 1. Yeah. This is supposed to be a 1. Yes. If n is even, this ends up being n over 2. So 6 would be like 1 2 3. Number of odd values less than or equal to 6. It's really the number of odd values that are less than or equal to 3, which would be n over 2. I think we divide by 2 again. It's a little odd, but I think that's correct. Okay, no. Now 1 1 negative 1. Oh my gosh, dude. This is this is like, oh my gosh. What's even going on? What is even going on? Number of odd values. uh, oh my gosh, man. hold on a second. Let me think about this for a second. So I want the number of odd values that are less than or equal to n divided by 2. If n is 5, we get number of odd values less than or equal to 2. N is 6, number of odd values less than or equal to 3. Which, when you divide number of odd values less than or equal to 3, so it's going to be plus 1, 2. Yeah, confusing, but that's the right one. 5 divided by 2 is 2. Number of odd values less than or equal to 2 is going to be 2 plus 1 divided by 2 is 1. 3 divided by 2 is 1. Number of odd values less than or equal to, divided by 6 by 2, you get 3. Number of odd values less than or equal to 3. 3 plus 1 is 4, divided by 2 is 2. You have 1 and 3. Yes, that's right. So there's a number of odd values that are less than or equal to. Okay. Then we want the number of odd values that are less than or equal to the sim value. Less than or equal to the sim value. Which should be actually sim value plus 1. And then we can take this difference. I realize this is very confusing. This is still wrong. Okay, of course it is. It's so brutal. It's so brutal. Oh my god. Oh, it's a rough one. It's a rough one. Let's try again. So for I is 0, we get the sim value of 1. Number of odd values that are less than or equal to 1 should be 1, which is what we get. This is less than or equal though. We subtract 1 because we don't want less than or equal, we want less than. That's why. Because when we subtract on the other side, odd count minus 1 minus 2, we want greater than or equal. Not just greater than. Okay. There we go. Now it's correct. Oh, it took so long. It took so long. How many hours did that take? Oh my gosh. Oh, it took like hours. It's brutal. It's very brutal. Okay. Now, the flat, so that's the flat even portion, counting the odd values. And then the odd portion we just had. So that gives us the flat amount. Okay, finally. That took a while. Now the rising amount is a little more complex. That's going to be we're not just counting the number of odd values now. Now we're taking the sum over those odd values. And these are not going to be the odd values that are greater than or equal. These are going to be the odd values that are less than. So now this is more like this odd count. It's similar to this odd count. So we're going to do odd count 3. Okay. This is going to be the number of odd values that are less than or equal to the sim value, which is going to be like this. And this one we compute a sum. Now, is it less than the sim value or less than or equal to the sim value? I think it's less than the sim value, not less than or equal. I think it's actually less than, which would be the same thing as this odd count, actually. So it's actually odd count 2. Whoops. And then we square that odd count too to get the sum over those odd values. And then yeah, and those are, we're not going to multiply with a sim value, by the way. Flat count and rising count, we add those together. Oh man. Is that complicated or what? Wrong. Amount 3. Flat count 1. Oh no, the flat count should be here, should be, oh yeah, this amount should be, well, the rising count might, oh, whoops, did that wrong. This is multiplied by 2, by the way. Okay, so now we get the right answer. Finally. Flat count 3, rising count 0, flat count 1, flat count, yeah, 2, and the rising count is 2. Gives you amount 4. And then 5, so you get 3, 4, 5, flat count of 3, rising count of 2. Amount gives you 5. Yeah. Because even though it's a 1, we multiply by 3 to get 3, and this other one's a 2. Okay, so that one's computed correctly, but the other ones are not computed correctly, which is annoying. 6, it should be 3. Flat amount is 2 for the first one, which I think is probably wrong. It appears twice, once in 1 and once in 2. So that's correct. Rising count is 0, flat count is, yeah, that's actually correct. It's 2 in both cases. Wait, they said this should be 3. 1, oh, but it's odd, the odd ones. Oh, I see. Oh, I see. In this case, you don't have 1, 3, 1. You just have 1. Oh, I see. Okay. It would be like 1, 2, 1, but the 2 and the 1. Yeah, okay. All right. That's a little bit odd. I think this works for cases that are larger than 1 and cases that are larger than 1 and 3. I didn't check what the test cases are. Oh, it's 1 to 1,000 only. Okay. Oh, it's wrong in this case still. Oh no. It's a bummer. Okay. So it's still wrong, but closer. About might take a minute to breathe here. It's a tough one, man. I could have just used the more basic approach and just went straight through, but like the quadratic time solution. But I believe there is a linear time way to do this. That doesn't use extra memory. It's just a little bit involved. It's a bummer. Okay. Let's try to fix these smaller cases first and see what happens. So, okay. These fly amounts are not correct. It should be 0 in this case. Okay. So 2 divided by 1 is 1, plus 1 is 2, divided by 2 is 1. So I get this odd count 1 of 1. And the sim value is 0. So this is wrong. This is wrong. Why should the flat amount be 0 here? The reason is the reason is that this wondering if this should always just be 1. You just always add this portion. Oh, excuse me. I'm missing something important here. So what I was suggesting was that in this test case, yeah, 5, 3, and 1 covers 1 once each time. So you want to count? Actually, maybe that's easier, is to just count the number of odd length subarrays that include this value. One does, 2 does, well, 2 does it twice. 3 does it 3 times. Or no, 3 does it twice. 4 does it twice. 5 does it once. That's kind of what I was trying to compute. That there are like different ways you can understand this, I guess. Oh man, I made it so complicated. There's probably a simpler way to think about this that makes it a lot easier. Yeah, that's what I was trying to capture there with the flat portion, was that like how many times do the arrays capture it more than once? Yeah, it's kind of a wonky way to do it, quite frankly. This gets captured once by size 1, and this gets captured once by size 1, and size 2 is just completely ignored. So would that be considered the flat part or the rising part? Well, the rising part, as I described, the flat part basically is the peak where um, the most subarrays cover that element. Um, so this one, only one of them covers it 3 times. This one is covered twice by 3. This is 3, 1, 3, 1, 3 times. And this one, it's covered by its maximum 3 times. This is covered by its maximum once, twice. Oh no, but it's an odd number of times, right? Odd length numbers. So this value is covered by its maximum. 3 covers it twice. And 4 covers it. No, and that's it. Actually, it's just 1 time. So this is just once, and then this is also once. This is covered by its maximum 3 times, though. All 3 lengths cover it. Ugh. What? Okay. Same thing on the other side. It's symmetric or mirrored. Then what about what about um the other arrays, how many times those cover? So this is all 3 of the subarrays maximally, right? Times 1. This is the first subarray, covers it once, right? Size 1. The size 3 covers it twice, and size 5 only covers it once. So it's 3, 4, 5, 4, 3. This one, it's just, there's only one subarray that matters. It's just 1, side length 1. This one, length 1, covers each one once. Length 3. Oh, you know what? Actually, maybe I should use a sliding window approach. Um, I don't think that you need to do dynamic programming here, though. I don't think so. Mm. Let me see something here. Let's see. Let's do some things. Okay. Let's do like 10, 15, 20, 3, 123. Let's just actually small numbers. 1, 2, 4, 5, 6, 7, 8, 9. Okay. Length 1, 1 plus 2 plus 5, plus 8 plus 9. Length 3, 1 plus 2 plus 3, plus 2 plus 3 plus 5. Um, 5 plus 6 plus 7. 6 plus 7 plus 8. 7 plus 8 plus 9. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4. Yeah. And this gives me something like the following: 1 plus 2 times 2 plus 3 times 5 plus 3 times 6, 3 times 7 plus 2 times 8. It's not. This is kind of what I'm trying to express here. That you can calculate this number directly. And then for 5, like 5, you get a very similar picture, but 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So you would go up to 3. So 1 times 1 plus 2 times 2 plus 3 times 5 plus 3 times 6 3 times 7 3 times 8 plus 1 times 9, or 2 times 8. Yeah, you get 1, 2, 3, and then it's kind of stopped at 3. And then these sums are going to be 1 plus 1 plus 1 times 1 plus 2 times 2 times 2 plus 2 plus 2 times 2 plus 1 plus 3 plus 3 times 5. Oh no, actually it starts off with this is initially a 1 plus 1 plus 3 plus 3 times 6. 1 plus 3 times plus 3 times 7 plus 1 plus 2 plus 2 times 8 plus 1 plus 1 plus 1 times 9. So this is kind of what I'm getting at. Result. Hopefully this makes some sense. Really love how you tackle each and every problem. Yeah, I appreciate that. Thank you. Yeah, absolutely. Deb Maller Desgupta, welcome. Yeah, oh yeah, I do everything. I do everyone, dude. I do every problem. Oh yeah. I do in the interest of time, like sometimes skip problems a little bit, but like I try to go through everything. I like will eventually return to problems if I have the time for it. But I basically like to do everything, yeah. Um, Thanks. Thank you. That's a big I'll take that compliment. That's a big compliment. That's something I strive for. So this is kind of what I'm getting at. Like I'm trying to visually understand like what these numbers are going to be in sequence. This is why I'm saying that I think this has a pretty clear pattern. It's not an obvious pattern, but it's a clear pattern. Like it's not obvious what it is, or it obviously has a pattern, but it's not obvious what the pattern is. I'm not sure to explain. I'm not sure if it's clear or obvious which one it is, but there's a pattern for sure, but it's not so obvious what the pattern is. And this is what I'm trying to get at is that independent of the numbers themselves, there's clearly a pattern that depends on n and the index that you're on. In this case, it's 3, 5, 7, and then 7 repeats 1, 2, 3 times. So maybe I can use that pattern where it'll go from 3, 5, 7, and it'll probably, if n is larger, it'll keep going up to 9, 11, etc. It'll just keep chaining an odd by an odd amount. Excuse me, starting with 3 being, I think, basically n plus 1 divided by 2. Um, so n plus 1 divided by 2 is probably where it starts, and then you add 2 at each element, and then when you get to somewhere in the middle, then you start subtracting 2. Then it stays the same, and then after a certain point you start subtracting 2. I would know. How do I know how far this should go? And is it correct that I would add 2 at each point? I don't think I had 2 at each point. I bet you it's a little more complex than that. So let's do. So I said 1, 2, 3, 4, 5. Oh, I'm not quite right here. There's actually 6 and 7 here. Yeah, I missed 7. There's one more element here that I'm missing. It does very much start to look like Pascal's triangle, doesn't it? Yes. So that's yeah, I missed 7. So we have 1, 3, 5, and 7 here. So I forgot 7. Like 7 repeats. That's also some of the symmetry that I was describing before too, that like the the lengths like 1, 3, and 5 and 7 are actually equivalent to each other. So you could just do 1 and 3 and then double it, and you'll get the same answer. But this ends up being 4, 6, 8, 8, 8. But let's do something a little more complex. Let's do whoops. Hopefully I can do this. Did it work? Oh, it did. Okay. Let's do let's do like this. X1, X2, X3 with X0. X4, X5, X6, X7, X8. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, now if I do 9 elements, I'm going to get 9 times 1 times x0. Now this is going to increase to, I think, 7 times 2 plus 2 times x1, which is kind of what I was trying to capture before. Yeah, and then this one is with the flat part. This is kind of what I was referring to with the flat part. This is going to be 5 times 3, I think, plus 2, x2. Is that right? 5 times 3 plus 2? Is that correct? Well, how would I say there's going to be 1, 2, 3, 4, it's 1, 3, 5, 7, 9. I'd expect a similar thing for 1, 3, 5, 7 as this pattern, but then a 9 there. So I was wrong. There's not going to be 9 ones. So it's going to be 1, 2, 3, 4, 5 ones, not 9. 5 ones. And then 2 of those ones are going to be relegated here. And so I'll have 3 2s, not 5 2s, or not that many 2s. And then I suspect I get something like this. So is it right that I get these 3 times 5? Yeah, I do. 3 times 5 here. And then length 5. Length 5 repeats, I think, length 3. Yeah, it repeats length 3. Let me see. Actually, I think I think actually it's not going to be 3 times 2. It's going to be 3 times 3 here. On length 3. Yeah, interesting. Oh, wait. So that's confusing, right? Maybe I should go through it again. I still don't quite have the pattern yet. Okay, let's try this again. We're going to say, oops. Scala draw kind of moves me all over the place here. So x0, x1, x2, x7, x9, x8. That's like the first one looks like this. The second one, when you have 3, you have x0, it's x1, it's x2, then x1, x2, x3, x2, x3, x4. And we're just going to say dot, dot, dot. Okay, and the results should be x0 times 1, 2 times x1, 3 times x2, 3 times x3, 3 times x4, x5, um, three times x6, Excalibur kind of moves my cursor around in a way it's a bit odd. X8. Interesting. So length 5 is different from length 3 in this case. This is going to be, so length 7 repeats length 3 with times x0 plus 2 times x1 plus 3 times x2 plus 3, 3 times x4, 3 times x5 plus 3 times x6 times x7 plus 1 times x8. Length 9 repeats length 1 with x sub 0 plus x sub 1 plus stuff like that, x sub 7, x8. Length 5 is going to be x0, x1, x2, x3, x4, 1, 2, 3, 4, 5. Plus x1, plus x2, plus x3, plus x4, plus x5. x2 plus x3 plus x4 plus x5. Plus x3 x5. That was only 4. X6 x6 plus x7. Which gives me 1 times x0 plus 2 times x1 plus 3 times x2 plus 4 times x3 plus 5 times x4 plus 5 times x5 plus 5 times x6 plus 5 times, no, not x7, no, it goes back down to 4, x7, actually I think it goes down further, x8. So it should actually go down to 1 here, 2, 3, 4. Okay. So this is kind of what I meant by the flat part, was that this section where it's 5, this other section where it's 3 across, this is kind of what I was referring to. So this is interesting, right? So now the 4 things that we add together for 1 is going to be 1 across, or no, it's 5. It's 5 things. So x0 looks like that. x1 is going to be 1, 2, 3, 2, 1, I think. Well, that's length 5, 7. Yeah, length 5 is peculiar. So length 9 and length 1 are both 1s. Length 3 and length 7 are both 2s. And length 5 is interesting. Length 5 I think is also a 2. No, length 5, yeah, on x1 it's a 2. Yeah, this flat part. On x2, things start to increase, gets interesting. It's 1, 2, 3, 2, 1. X3, I think, starts to get to be. What is x3? Like 1. X3 is 1 plus. X2 is 3. X3 is 3. On the next one. That's length 3. And length 5. It's also. X3 is 4. And X3 at length 3, I think it's 3. Interesting. Okay. And then x4 becomes 1, 3, 5, 3, 1. And then starts to repeat. Oh, this is incorrect. This is a 2. Something's wrong here. Okay, we got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. This last one should be all ones. Actually, I think these are. Yeah, something like this. X1 is all 2s. Yeah, I think X1's all 2s. That means this one's all 2s also. And what about this one? These should mirror each other. X2 and X6 should mirror each other. Yeah. So that's a bit odd, right? I mean, that's quite the pattern going on there. So, is this correct? Is the question. Let me try to double check this. So, set length 1. It's 1, 1, 1, 1, 1. Or no. 1, 2, 3, 4, 5, 6, 7, 8, 9. Length 3. It's 1, 2, 3, 3, 3, 3, 3, 2, 1. Length 5. 1, 2, 3, 4, 5, 4, 3, 2, 1. One, two, three, four, five, 6, 7, 8, 9. And then this repeats, right? Okay. And then if we add those down, you get 1, 2, 3, 4, 5. 1, 2, 2, 2, 3, 1. 1, 3, 3, 3, 3, 1. 1, 3, 4, 3, 1. 1, 3, 5, 3, 1. 1, 3, 4, 3, 1. 1, 3, 3, 3, 3, 1. And 1, 2, 2, 2, 1. Okay, that's the pattern. Now how can I compute that a little bit more directly, right? If that makes sense. How could I excuse me, I went way too far down. How can I encode this in a more generalized pattern is the question. I mean, these ones are obviously just n each time, the ending ones. The middle ones are a little more complex. It's 2 multiplied by across, 3 multiplied across. But then there are these kind of, it's sort of like this rising intersection that occurs. Um, like, what does the pattern look like for um, 10 and 11? Or just 11? So if we added 2 more elements, right, clearly we know what these are going to look like. But it's less obvious what the internal parts are going to look like. So this will probably be very similar, right? Add 3 there. This will go up to 5 and add 5 here. This will go up to 7. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's too many. Hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7. I think this will go up to 5. The reason why I think this caps out at 5, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, the reason why I think this just repeats at 11 is because, like, you add 7 across, 1, 2, 3, 4, 5, 6, 7. You can only, I think you cap out at like 4 or something here. Right, so 1, 2, 3, 4, 5, 6, 7. And then it would be that one, 2, 3, 4, 5. Yeah, it caps out at 5, I think. I think it just repeats. Which is a little bit odd. I wasn't expecting that, but that's probably what happens. And then these patterns repeat. That's probably what occurs. Oh, this one should be. Okay. So then these end up being a similar pattern that we saw before. Twos across, threes across, but then we have ones, threes, fours, threes, ones, and then ones, threes, fives, threes, and ones. It's a weird pattern. It's a weird pattern. Whatever I was doing before, I don't think captures this pattern, by the way. I don't think so. That is a strange pattern. I think this is the right one. Hmm. Hmm. Yeah, the cap is going to be the length minus whatever sequence you're working through plus one. Um, and minimum of the length itself, and then that difference that I just described, which is n minus the length plus one. So in this case, it's 3, right? 11 minus 9 plus 1 is 3. And then in this case, 3 would be the minimum of those two. And then these values are just going to rise up to that cap and then stay there and then fall back down. And that's the clear pattern that every sequence is going to follow. But then I've got a sum in the other direction across those sequences. So even those sequences have a very clear pattern. The sum across those sequences, the cross section of those sums of those sequences is not as obvious. So it kind of bubbles up. It's like repeated ones, then repeated twos, then repeated threes, then some 1, 3, repeated fours, and then back down 3, 1, and then 1, 3, 5, 3, 1, and then this part just repeats a few times. This middle part, and then you have the same sequence again. 1, 3, 4, 3, 1. So a bit odd, a bit odd. Yeah, interesting, very interesting. Huh. Uh, I could take the previous value and increment or decrement depending on where we're at. So the first value starts off at n. The next value we add n minus 2. The next value at n minus 2 again. The next value, it's n minus 4 gets added. Then n minus 4 gets added again. Then we repeat that value twice. Then we subtract n minus 4, and then subtract n minus 4 again. Then subtract n minus 2, and then subtract n minus 2 again. Okay. Interesting. So what does that look like? There's 3 sections. The first section is going to be start off with n. And we say, okay, result plus equals. Let me put this up at the front so I can go back to my notes easily. Okay. starts off at n equals 1. Now we're going to add n minus 2. Okay. Yeah. Add n minus 2. Then we add n minus 2 again. Okay. Oh no. It's value times array of I, array of 0. Then value times array of 1. Array of 2. So we said n minus 2. And then we add n minus 4. So add n minus 2. Start off with n. Add n minus 2. Add n minus 2 again. Add n minus 4 here. Do that again. Then maintain that 2 more times. Then subtract n minus 2, n minus 4, subtract what we just added. And then subtract again. And then subtract n minus 2. And do that again. And that will give me 0 through 9. It should be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Should be 11 things I had here. N, so we would do n, add n minus 4, add n minus 4, or excuse me, add minus 2, add n minus 2, add n minus 4, add n minus 4, leave it once, leave it twice, subtract n minus 4, subtract n minus 4, subtract n minus 2, and then subtract n minus 2. One, two, three. Once, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm missing something here. So start with n, that's once. Add 1, add 1, add 1, add 1. So it's plus 1, plus 2, plus 3, plus 4, 5, 6, subtract 1, 7, subtract 2, 8, subtract 9, subtract 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0, 1, 2, 3, 4. Oh, that's where I'm stuck. I was gonna say, I was like, wait a minute. Should have this fully described here. Okay, yeah, there we go. I was gonna say, I was like, I think I did this right so far. So these are 3 different sections, right? This one is the increase or kind of increasing section, and then this is the decreasing section. Yeah. Or non-increasing. So not changing, decreasing. This is for the n equals 11 case. It looks like this. Excuse me. So let's try to emulate this now. Let's do val I0. Start with I, and then we're going to add equals, and there's this other value j. Starts off at 0. Starts off at 2. And we're going to plus j plus equals 2. We're going to do that. It's actually going to be in steps. So we actually repeat j twice. So we're going to say something like this. Only when I is a certain value, so when I is even, we don't multiply by 2. We could do 2 minus or something like that. So if it's odd, how does this work? I might have to do the other way around. Something like this. But when it's when I is odd, that's when we want to. J starts off at 2, right? Yeah. So initially we don't touch J, or we don't touch the value, and then we add. And then I should be even, I should be odd. We're going to increment now. So that way when we iterate again, oh no. Actually only when I is even again. So if I is even, 0 minus 2. I think it's supposed to be the other way around. When I is even, this will increment by 2. When I is odd, this will increment by 0. Okay. And then, so what's going to happen is we get, initially, we decrement the value by 2. Then, so it's just val of array of 0, then decrement by 2. because this is even, or increment j by 2. No, I actually becomes odd after that, so we don't increment j. And then now when I is odd, we don't touch j. It's a bit confusing. It's a bit confusing. Let's do it this way. Actually, this is a little bit easier to think about. There we go. Let's do it this way. It's confusing. I want to modify value first before I apply it. Let's do it that way. So initially, val increments by n flatly, and j is 0. And then when we modify I 0, and then now here, let's do j first, and then increment I. And we can say when I is odd, when I is even, then this will add 2. Okay. So now we add 2 to j, add n minus 2, I is now 1. We do perform this routine, done. Now j doesn't change, I increments to 2, perform this routine, so we subtract the 2 again from j. I is now even at 3, I think. When I is 2, before it increments, we add this again. Now we have 4, I is 3. Okay, so this will work. But now we get to 5, so that's when I is less than or equal to 4. We want to do these routines. What's interesting about this is, we'll come back to that. There's now this next set of things, which is I is greater than or equal to 5, and I is less than or equal to 6. Increment I, and just say result plus equals value times array of I. Right, that handles these cases. And then finally, the mirrored version of this is going to be the decreasing part. I is greater than or equal to 7, and I is less than or equal to the array dot size. So we're going to use this for the rest of the way. So now it's subtract n minus j, and here j starts off exactly where it was before, at 4. And I at this point is 7. And we would apply n minus 4 to 7. And then j, we want to increment now, or decrement now, actually. When I is 7, this doesn't change. So yeah, this gets applied twice. Doesn't change until you see 8. And then decrements again until you get to 9, 10. And then we're done. And that's it. And that works for the 11 case. That's exactly correct for the 11 case. I suspect this is correct for all the cases, quite frankly. If I just modify I, so here this went from 0, 1, 2, 3, 4, which is the 5th element. First 5 elements. Then we had 2 elements where it didn't change. And then the last, I guess, 5 elements, or last 4 elements, I suppose. Um, Interesting. So, how do I know what this should be? Well, compared to 11, this is like 11 divided by 2 would be 5. It'd be like less than 11 divided by 2, less than n divided by 2. And then it'd be greater than or equal to n over 2. Um, I think this is only 3 elements, quite frankly, in the middle. Typically, 1 to 3 elements. Let's look at 13 so I have an idea. Better sense of things. What happens with 13? How's that chat doing? What's up, chat? What's up, chat? Okay, 13 is going to be a copy of, so here we'll add another 2 elements. By the way, I didn't cover what this looks like for the even cases. I think it's very similar. I suspect it's a very similar thing. For 3, it's just going to be this. Actually, I should just copy this. For this is going to be 11. Oh, what happened? I should probably just do that. Okay. 5, 1, 2, 3, 4, 5. 5 repeated. This will be the same for 7 or 9. And then 7 is going to be 1, 2, 3, 4, 5, 6, 7. 6, 5, 4, 3, 2. 8, 9, 10, 11, 12, 13. Yeah, so this is going to be this sequence. So again, n minus 2, add n minus 2, add n minus 2 again, add n minus 4, add n minus 4 again, and then add n minus 6, add minus 6 again, n minus 6 again. And then you would have okay, I see the problem. And then you would have subtract n minus 6, subtract n minus 6 again, etc. So actually, there is no middle section. What happens is this basically just becomes 0. and the j becomes equal to n. You're just subtracting twice n minus n. That's what's going on here. So this is indeed I of so in this case it would be 0, 1, 2, 3. Or no, it's going to be 0, 1, 2, 3, 4, 5, 6. I think all the way up to I equals. In fact, I think you actually just go, you're not subtracting n minus this thing anymore. I think this just goes all the way through. Yeah, I actually think this is just all the way through. I could be wrong about this, but this might just be all the way. It might just be that simple. I don't know. Oh, okay. Maybe not. Not quite. That's funny. Whoops. Uh-oh. What did I do? Huh. Interesting. Uh-oh. Uh-oh. Huh. What? Can make this a long. I did something wrong. But it might just be that this value starts to exceed n at some point. Like the j starts to exceed n. And actually wait, what? What is going on here? Oh, not less than or equal. Duh. That's my fault. I was like, wait, I did something wrong here. 158. Well, that's not right. That's not right. These are way too large, huh? These are way too large. Hmm. Um, oh, it's not n, by the way. That's a mistake. It's n divided by 2. 1, 2, 3, 4, 5, 6, 7. Yeah, it's like n plus 1 divided by 2. And if it was 14, it would be 2. Or no, if n was 14, it would still be 7. Length is 13, it's 7. So you add 1 divided by 2. And say we'll just say odd lengths. That may have had something to do with it. Okay. It's closer. It's wrong in the even cases, though. Whoops. In the even cases, it's wrong. Let's do the four case. I was close, man. I was close. I seem to have figured out the pattern when it's odd, at least. All right, let's go even. So in the 4 case, length 1 and 3. I think it's just this. You sum all 4, and in the 3 case, it looks like this. Yeah, that's a little different. Uh-huh. It is different. Okay, give me one moment. Okay. All right. The even cases are different. I was so close, man. I was so close. Okay. All right. Length 1, length 5. This is if you have 6. Okay. It was 1, 2, 3, 2, 1. Uh, all right. Definitely 1, 2, 3. So the third value, the first one, 1, 2, 3 has the third value in it. Second one has the third value in it, and the third one has the third value, and then it's capped at 3. Yeah, so that's repeats. And this one is, so that pattern I just showed you is only for that's only for, hi, what's up? Yashinda. Oops, hope your day's going well. Welcome, howdy. So we're investigating right now how I could solve this question, sum of all odd length subarrays, in linear time, but also linear memory, meaning we're going to do it without using dynamic programming. And I think there's a way to do it, but I've been struggling to get it right. So I think I got the odd case, but I don't think I got the even case when you have an even number of elements. Looks like the odd case is right, but the even case is not, doesn't work the same way. So I'm investigating the pattern for the even case, see if I can find out what that pattern is. Using pattern recognition to see if I can figure out what the pattern is for the even case. All right, here we go. So in the even case, with 4 elements, this is more of what the pattern looks like. We add, this is like if it was x0. I probably should put that at the top, actually. I'm so used to doing it at the bottom. I don't typically use Excalidraw for my notes. I use a different program typically. I should write a notes program or something. Just write something for myself. That way I just always have it available. I can open source it and then people can use it. It's like Notepad, I guess, but more for my use cases, I guess. I don't know. Excalidraw is pretty good though. Just isn't quite what I want to use. You know, it doesn't quite flow the way I'd like it to flow, I guess. I don't know. I like to adapt to it. Anyway, but so if this was like x0, x1, x2, x3, right? When we're looking at length 1 subarrays, we would be adding each of these one time, right? So 1, 1, 2, 3, 4. But for length 3 subarrays, we'd add 1, 2, 3 here, and then we're adding 1, 2, 3 there. So we would have this one twice and this one twice. That's why 1, 2, 2. This pattern is not the same as the odd pattern that I had before. The odd pattern that I had before is a little different. In the case of 6 elements, the pattern looks more like this. So in the odd case, so the first one length 1, length 3, we would have 1, 2, 3, back down to 3, 2, 1, and then length 5 actually repeats that. It would be length 5, 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. It actually is not this pattern. This is wrong. It's this pattern. That was wrong. 1, 2, 3 here. 1, 2, 3 here. So x1 has 2, and then 1, 2, 3 again. x2 has 3, but also x3 has 3 because it's at the tail end of this one, and it's in the middle of this one. And then x4 similarly. It's included here, and it's included here, and nowhere else. So actually the pattern, a little more complex than the other pattern. So I got to figure out what that pattern is. So I think what I can do is say, do the following. Don't need this. This doesn't need to be a long. I thought it needed to be because I was accident. I made a mistake and I made a mistake and I was adding like uninitialized memory with this with an equals there. Which is bad. But this is going to be if array.size and 1, then we're going to do this. Otherwise, we're going to do a different pattern. In the even case, pattern looks a little more complex. It looks like let me also check the stream health just to make sure stream is okay. Looks all right. All right. In the even case, it looks like I start with n, similar to the previous pattern, where n is I say n, but it's really this odd lengths value, which I think is the same. So when the size is 4, add 1, divide by 2, and you get 2. When size is 6, add 1 divided by 2, you still get 3. Yeah, that's fine. So this is the right odd lengths amount. So we start by adding odd lengths, which is fine. But then we add, it looks like odd lengths minus 1 rather than minus 2. Okay. Yeah. So j plus equals 1 rather than 2. And then, oops. Oh. Looks like we subtract 1 initially. And then I think we subtract 1 again from j. Yeah, which, there's the 1 there. And subtract another 1 because we're only going to improve here. And then subtract another 1 and then just keep subtracting. So just subtract 1 the whole way through. Okay. I don't know about that one, but I can try that. That doesn't seem correct. Oh, that's right. Okay. There you go. There you go. There's your pattern. Ta-da! I did it. Ta-da! All right, I'm gonna go for it. That's probably correct if it works on those cases. Hey, there we go. Beautiful. I like that. I like that. Hey, we did it. Spent hours on that. Oh my gosh. Oh. So unnecessary, but there you go. They asked for a linear time solution, so we got linear time and no extra memory. Ta-da. Ta-da. That was a little gross. That was a little gross. I wouldn't recommend that. That's like, this is like when you want to do research, this is the kind of thing you do. You just tinker with stuff until you find a pattern that you can exploit. That's how you do research, man. That's how it works. Tinkering until you find an exploitable pattern. Oh, which doesn't sound great when you phrase it that way, but say a useful pattern. Exploitable pattern. Exploitation. No. Yeah, okay. It's just satisfying to submit it a bunch of times. I spent so much time on that. It was so unnecessary to spend so much time. It was interesting though. I mean, we learned something. I don't know what we learned exactly. We learned that yes, this does have a pattern. Yes, that can be useful. Yes, it can be done in linear time. Yes, it can be done with constant extra memory. Yes, it's a bit complicated. Yes, it does simplify to something that's actually not too bad. And yes, it will take basically research time to figure all that out. I don't know how valuable all that information is, but I guess it's something. I don't know. I don't know what to say, man. I don't know what to say about this, man. Um, that was fun. I guess that was fun. So I got there. Sweet. I don't know. What do I do now? I just keep going. Um, I feel like I should take a break. Oh, how's the stream doing? The stream is. Let's see. Is it still live? The stream might not be up anymore. I feel like I should take a break. Oh, how's the stream doing? The stream is. I think it says the stream is. Okay, there we go. It's back. I was gonna say it says the stream is. It was buffering. So there we go. We got that answer, man. Got there. Do one more. Oh, satisfying. Very satisfying. Okay. Wasn't really necessary to do all that, but we did it. We did it. We did it. All right. Okay. We'll do one more question, I think, and then maybe I'll take a break. I was gonna do an 8-hour stream, but I kind of like, I don't know, man. That was a bit much. That was a bit much. Let's do one more, and then I'll think about what to do after that. Zero index integer array nums of length n, integer k, return the number of pairs, 0 less than or equal to I less than j less than n, such that nums of I equals nums of j, and I times j is divisible by k. Okay. The number of pairs divisible by k. All right. Okay, well, this isn't that hard, right? Basically, any number that's divisible by k, all of the numbers to the right can be paired off with k. And you can do left to right. So you don't need to go backwards at all. Yeah, so that's the easiest way to do that. So you can just do something like the following. It's going to be nums of I mod k 0 times nums.size minus I possibly plus 1, something like this. Like if you pick the third, if you pick the, let's say the first element, it's going to be paired up with every other element except for itself, right? Oh, wait. Oh, nums of I equals nums of j. Oh, hold on a second. Oh, no. Oh, that's a little bit different. Never mind. So I did that wrong. Oh, all right. Okay. How big are these numbers? It's a little bit, it's a different approach I need to take. Okay, they're between 100, less than 100, so I can use a frequency map. We're going to use a frequency map to do this. I did this, I got the wrong answer. Sorry about that. I misunderstood. I misunderstood. We'll come back to that. Explain. All right. Actually, it's a little different. So frequency of I, nums of I. And it's actually going to be nums of I mod k equals 0 times, it might be a little bit easier actually. I think it's this one is the way to do it. This is a bit of an odd problem. Wrong. Okay, I misunderstood. This one's correct. No, it's wrong. Case 2. So it has to be, yeah, so basically I'm looking at the values previously. So when I see 3 and 3, that should be 1. I'm saying expected 4. When I see 1 and 1, that's not divisible by 2. 2 and 2, so the first two, there aren't any previously, so we'd add 0. This 2 and 2, we should add 1, and then this 2 and 2, we should add 2. So it should be 1 plus 2 plus 3. Why am I getting the wrong answer? Shouldn't I get the right answer? Shouldn't this give me 4? Frequency of nums of I, which should be, say when you see 2, it should be 0. When you see the next 2, there should be a 1 there. So you add 1, and then frequency becomes 2. See this, you add another 2. And then this adds 0, this adds 1. Yeah, it should be 4. Why did I get 3? Unless there's something going on here I don't realize. Oh. What? What? What's going on here? What's going on here? So it should be 0, 0, 0, 1, 3. Okay, that's good. 1, 3, and then 0, 0, 0, 1, 3, 3, 4. Oh, those aren't divisible by 2 either. Oh. Oh, I see. Wait, why is this 4? Wait, what? 4 pairs. Oh, if it's 0, wait, what? Oh, I'm sorry. I think I do need to take a break. A brain, dude. My brain, man. Oh my gosh. Oh my goodness. I didn't even realize it's I times J is like oh boy. Yeah, I need a break. I need a break. It's a mixture of going too quickly and also not really thinking it through, reading the problem. It's good to solve the actual problem that's being asked. Oh my god. Yeah. Okay. Uh, interesting. This actually is pretty close, but it's okay. I think I could still use a frequency map, but I need I times J is divisible by K. So as long as one of these is divisible by K. Yeah, it doesn't matter if they're both. Yeah, actually, this is fine. It's just I mod K. I think one small change and this works. Let's find out. Maybe this actually might be that simple of a change. No. Nope. Output 3, expected 4. No. Nope. Okay. Interesting. Doesn't quite work like that, unfortunately. Yeah, the problem with this is that no, this approach doesn't really work. In this case, it's wrong because I've already passed 3. Like this 3 could be paired up with all the other 3s. Could do it a different way. How about I just take all of the ones that are I could maybe do 2 passes. I mean, I don't know. uh, I'm wondering if I could do a double pass. Well, I mean, I could double count all the pairs, right? I could do IJ and JI. I just count all of the. If I could just get the frequency of values, for example, the frequency of 2 is a 3, and then I just say, oh no, it's not. Yeah, well, I just get the frequency of all these values, right? And then I go left to right for each value that's divisible by K. I pair that off with all the other ones. So, 2 minus 1 would be 1. And then when I went over this way, I wouldn't count it again. No, that's not correct. Excuse me, that's not correct. I'd have to get the frequency of things that are divisible by k and things that are not divisible by k. Where the indices are divisible, the indices are not. Because it's going to be the indices that are divisible, I would do like to choose those indices. And then the indices that are not divisible, I would need to pair them off, which I would just multiply those two. Yeah. Okay. That's fine. That works too. Okay. Frequency divisible, and not divisible. And frequency no. Let's go with this one. Oh, I can make these static. I don't know if that really matters, but we're going to do that anyway. So for each number, we're going to say frequency divisible const check is I mod k equals 0. And then we're going to say frequency of nums of I plus equals check. It's divisible. Frequency not. It's minus equals check. Or plus equals check. It's not. Or not check. And then we're going to say for int I 0 is less than equal to 100. Result plus equals I mod. So again, constant check. I mod. Oh no, that doesn't matter. No. Frequency of divisible I times frequency of divisible I plus 1, bit shift 1. So pair those off. And then the other one will not be paired. Just multiply it. I think that's it. Something like that. I'm going to go for that. See how that goes. Hey, bro. How are you? What's up, devotee of Radharani? Welcome. Howdy. Hello, hello. Doing well, man. Thank you for asking. Doing some LeetCode over here. Apparently getting it wrong, though. No. Oh, no. What did I do? What happened here? Uh-oh. Huh. Wow. Interesting. I don't know what I did wrong. Uh-oh. Uh-oh. Oh, I might have been in choose too. I might have been not. Yeah, that's a mistake. That might have been a mistake. There we go. Got it. Okay. I think that's it. I'm going to submit this one. That's a relatively efficient solution. It's an okay one. Oh, it's wrong though. No. Oh man, that's a bummer. All right. Almost efficient and wrong. And wrong. It's always good. Oh boy. Oh boy. Tisk, tisk, tisk. Okay, let's see. Huh. Output 5, expected 8. Interesting. All right. Let's see if we can get those pairs. Now, mind you, this could be done in quadratic time efficiently because there's only 100 questions, 100 integers, but part of me thinks this could be done with a frequency map a little bit faster, so that's why I'm trying to do that. But 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 elements. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13. 13 elements means there's only 3 elements here that are divisible by 4. 3 indices. But they can be paired off with quite a few other things. But there's only one 9 and one other 9. So 2 9s, which the second 9 is actually in the I don't know, 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. And the second 9 is not. So I pair those two off. That gives me one pair. It says they're looking for 8 pairs. 4, 5, 6, 7, 8. Okay, this 3 can be paired off with 1, 2, 3, 4 things. I would get 1 plus 3 is 4, and then one more would give me 5, which is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's nothing that would be paired off with a 1. There's only one 1 here. I times j is divisible by k. 0 indexed. Huh. 0, 1, 2, 3, 4. That's 9. Only one of the 9. So that's and that happens to be a pair. That's a pair. And there's 1, 2, 3, 4 threes. 0, 1, 2, 2, 3, 4, 5, 6. Oh, I did it wrong. Oh, I did it wrong. I didn't think about when k itself has divisors and you multiply I and j together and it's divisible. I thought I could just that's a mistake on my part. Yeah, there are more pairs. Also, my calculation was wrong anyway. Somehow it shouldn't have been. Oh, I guess it was 5. I guess 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think the 8 here, we get 1, 2, 3. I don't know why I got 5. I think I was supposed to only get 4 there. But anyway, I don't think my algorithm was correct. Like, I don't think my implementation of what I was trying to do is correct anyway. But also, I did not consider when k is a composite. Ooh, that's a mistake on my part. That's a mistake on my part. Okay. I mean, yeah, that's a tricky one. All right, we're just gonna go with the norm. I don't think it's that obvious whether or not this has a faster approach. So that was a mistake on my part. We're just gonna go with the standard approach, straightforward approach. Oops. Yeah. Given the constraints, this is fine. I think this will work. I might need some things in here. Okay, it worked. I would put these in here just to clarify things. Yeah, given the constraints, this works, but if the constraints were a little more complex, then this may not work so well. Dang, man. Dang. Yeah. All right. I said I was gonna take a break after this, but that kind of I'm not so sure about this one. Let's see. Um, okay. Yeah, I think I just gotta feel bad now. Feel bad for trying to get a better solution that was probably not correct. It's awkward. I mean, okay, all right. Given the constraints, this is a reasonable solution. So we'll go with the next question. We'll go one more. We'll go one more. And then I think I'll take a break. That one wasn't too satisfying. Yeah, it was a bummer. Not a bummer, but like not great that I submitted an incorrect solution there. There's a biker going on a road trip. The road trip consists of n+1 points at different altitudes. The biker starts his trip on point 0 with altitude equal to 0. You are given an integer array gain of length n, where gain of I is the net gain and altitude between points I and I+1 for all 0 less than or equal to I less than n. Return the highest altitude of a point. Okay, going on a trip. Road trip consists of n+1 points at different altitudes. This trip at point 0, altitude is equal to 0. Integer array gain of length n, where gain of I is the net gain and altitude between points I and I+1. Okay, the highest altitude. I'm not sure we can do this in better than linear time. Yeah, I mean, I think this is just. All right, we'll see. Um, I don't know. I think it's probably a relatively straightforward thing. I mean, is this? I don't know. This is all I need. I'm not sure if this is what they're looking for. Just pretty simple. Maybe this could be done like in simpler way, but I don't. Or a more what do they call that? Could be done in a more concise way. I don't know. I mean, all right. Okay. That one, I don't know what to say about that one, man. I don't know. That was definitely a little bit easier. Well, these are all relatively easy, I think. It depends on how you try to solve them, right? Positive integer n, find the pivot integer x such that the sum of all elements between 1 and x inclusively equals the sum of all elements between x and n inclusively. Interesting. So basically the left side and the right side, but it's not pivot integer. It's I think, or it's not the left side, the right side are equal. I think it's every element that's smaller. Unless x is an index. N is 8, up 6. Oh no. Oh, excuse me. Oh, I see. Oh, interesting. I think you could figure out this mathematically. At most one pivot. Okay. Oh, interesting. Okay. So this is a math thing, I think. If you do Let's just make sure the stream is still live. It's okay. Yeah. Okay. So this would be 1 to n, right? We're gonna say 1 to x plus 1 to n. It should be equal to each other. More precise notation I'll put down in a second, but it's okay, equals x to n inclusively. Okay, so it's going to be, it's not x plus 1, it's inclusive of both sides. So this is kind of like sum. I actually didn't realize that 1 to x is equal to the sum of x to n, which this sum is it's x times x plus 1 divided by 2, and that's going to be the sum n times n plus 1 divided by 2 minus the sum from 1 to n minus the sum from 1 to x minus 1, which is x minus 1 times x divided by 2. So that gives you x times x plus 1 divided by 2 plus x times x minus 1 divided by 2 equals n times n plus 1, 2. Can multiply everything by 2 to get x times x plus 1 plus x times x minus 1 equals n times n minus 1, n plus 1. Then gives you x times x plus 1 plus x minus 1 is n times n plus 1. Then gives you x times 2x equals n times n plus 1. So then gives you x equals x squared, 2 times x squared plus 1. X is then equal to the square root of n times n plus 1 divided by 2. Yeah. Okay. Return static cast int square root n times n plus 1. Basically that. There might be, I think, yeah, it should be a -1 in some cases though. It's not that easy to check if a number is a perfect square, however. Probably the easiest way to do this is int result. So we have this number, and then we say 2 times result equals n times n 1. Say if bit shift. If this is equal, or it's not equal, turn it equal. Otherwise, return something. There we go. Simple. There we go. I think that works. Nice. Sweet. Yeah, so that's not a bad one either. I'm not sure if it's exactly constant time, but it's relatively efficient. It's a relatively efficient solution. That's probably a good one to end on for the not end on, but take a break. I was gonna go for a full 8 hours, but some of those questions took a really long time. Delete node in a linked list. Oh, this is a complex one or involved one. This one is, I already solved it, so I'm not going to do it again, but this is one of those questions that it's kind of involved. Okay, they said it's not going to be a tail node, and so literally about 2 million accepted. Holy smokes! Oh my gosh, it's a lot of people. Holy Jesus! Holy smokes! That's a lot of people. All right. Given the node to be deleted, cannot be given access to the first node of head. All the values linked list are unique. Given node is not the last node. Delete the given node. Do not mean removing it from memory. Should not exist in linked list. Number of nodes in linked list should decrease by 1. All the values before node should be in the same order. For input, you should provide the entire linked list head and the node to be given node. Node should not be the last node on the list and should be an actual node in the list. We'll build the linked list and pass the node to your function. The output will be the entire list after calling your function. Unfortunately, you need the node in front of this one, the previous node, to do this efficiently. Otherwise, you basically need to like traverse the list until you find your node, which is kind of a bummer, but it's not the worst thing in the world. Yeah, and then you just do a normal delete, which is basically just put the previous node's next pointer to the deleting node's next node. A little bit involved, but not the worst. And then you want to take that node and then point it to a null pointer and then delete it from remove from memory. But do you get the head node? You will not be given access to the first node of head. What? Somehow I already solved this. I don't know. Oh, I see. Interesting. Well, I mean, the other way of doing this, which is a bit wonky, but you can, is so the node that you want to delete, let's say it's 5, you could just take all the values that come after it and just shift them over. I wouldn't recommend doing it and then just delete the last node, the tail node. Oh, that's why it's not gonna be a tail node. Is because you wouldn't be able to delete the tail node. So you can do that too. I mean, that's a bit awkward and weird, but yeah, you could do that. You can just cycle all the values back and then delete the tail node. It's kind of obnoxious, but yeah, it's fine. And then the tail node, you can delete the memory. So yeah, I don't know how I solved this in the past. Probably I did it in Python in March. But to 2019. It's a long time ago. I think I basically, I suspect I may have cheated. Oh no, I did exactly that. Oh wait, what did I do? I don't even remember doing this. I said the node value is going to be the next node, next, and then the node next. Oh, that's clever. Oh, I see what I did. Uh, no, man, don't cycle all the values. Just move the value. Oh, that's smart. So just take the next node's value, save it in this node, and delete the next node. That's funny. I didn't even think of that. That's even better. Oh, jeez. There you go. That's a fun one. Okay, so that's that one. That's kind of goofy, but yeah, it's okay. Don't cycle all the other values back. Just save the value that's next to it, and then delete that node. It's funny. Okay, got it. All right, we'll do one more question, then we'll take a break. All right, arithmetic subarrays. The sequence of numbers is called arithmetic if it consists of at least two elements and the difference between every two consecutive elements is the same, or formally a sequence S is arithmetic if and only if S of I plus 1 minus S of I is equal to S of 1 minus S0 for all valid I. Okay. Arithmetic sequences, all right. These arithmetic sequences, the following sequence is not arithmetic. You're given an array of n integers, nums, and two arrays of m integers, each L and R representing the m range queries, or the ith queries the range in the range L of I, R of I. All the arrays are zero indexed. Return a list of Boolean elements, answer where answer y is true. If the subarray nums of L of I to L of I plus 1, etc., can be rearranged to form an arithmetic sequence and false otherwise. Wow, that's confusing. What are the bounds in this? N numbers, M is L length, M is R length, N is 500, M is 500, L of I, R of I is less than N, numbers between negative 10,000, 10,000, 100,000, 100,000. I don't know what I'm even looking at here. It's arithmetic, consists of at least two elements. Okay, got that. So these are sequences, array of integers, and two arrays of m and m integers each, L and R, representing the m range queries. Okay, so we got range queries, ith queries that range, all the arrays are zero indexed. Return a list of Boolean elements, answer, where answer y is true if the subarray nums L of I to nums R of I can be rearranged to form an arithmetic sequence and false elements. Okay, well that's peculiar, huh? I mean, probably the easiest thing is to sort it and then check the sequence directly. There might be a more efficient way to do this, but that's like the simplest way to do this. Give me a range of 654. Excuse me, to the sequence. 4, 5, 6, 9 cannot. 3, 3, 5, 7, 9 can be arranged. Huh. I don't know if there's a more efficient way to do this. This is a bit of a complex kind of a thing to ask to do. You maybe can use like a square root decompositions, throw that somewhere in here to make things more efficient. I'm not sure where exactly or how, but that's like my best guess, is that maybe a square root decomp somewhere in here, and then otherwise, I wouldn't really know how exactly. And then maybe using hash maps or something, but probably the simplest approach is just for each query, sort that range, and then check if that's an arithmetic sequence and time linear the range. That's probably the simplest way to do it. The number of queries is only about 500 queries. The number of numbers is only about 500 numbers. So 500 squared is manageable. So we'll just go with that. We'll just keep it simple and go with that. I think doing something beyond that, it's unnecessary for the constraints. It's also like might be really complicated if it's even possible. Yeah, I think the other question that I was working on, where I was like, oh, I'm not really sure how I could do this. Like everything you work on, probably could throw a square root decomp in there somewhere. But the simplest thing is probably just copying the numbers and sorting them. So we can int I0 is less than size I constant left li, right is ry. Then we'll just say std vector int temp of nums begin left nums begin right. Sort temp begin temp end. We'll just say const auto is arithmetic. Take vector say if v.size less than 2, true false. Constant diff is going to be v1 is v0. Int I0. I really should be I is 1. I is less than I plus 1 is less than size. True. If v of I plus 1 minus v of I, is not equal to diff, true false. Okay. Std vector bool result of it's going to be l.size and just say result of I equals this arithmetic. In this case, I just copied the vector into a sub vector and then sorted it and checked it that way. It's so wrong. It's so wrong. 0 to 2 should be true. 4, 5, 6 is true. 0 to 3, 0, 1, 2, 3. 4, 5, 6, 9 should be false, but I got true for some reason. This might be a +1 over here. I might have made a mistake on that. Should be true at the end, but I got false. 0, 1, 2, 3, 4, 5, 3, 5, 7, 9. Hold on. What is going on here? Hold on. 6, 5, and 3. Wrong. It should be 5, 9, and 7. Okay. Let's try that again. Okay, good. So at least I have the right things. Then 0, 1, 2, 3, 5, 7, 9. Oh, it should be front, not from, but all right. 2 to 5, 0, 1, 2 should be 5 to 7. And it should be 4 to 5. And 4 to 9. Yeah, okay, that's all right. I don't know what happened. Oh, that's... My gosh, man. I didn't even realize I did that. That was a typo, okay. I was looking at it like, wait a minute, didn't I do this right? What did I do? All right. No more debug. I'm gonna go for it. See how it works. I'm gonna go for it. There we go. Beautiful. Beautiful. Not the fastest solution, but like reasonable time to solve it. I probably should have solved that a little bit faster. Let's see what the fastest solutions look like. I'm curious. I am curious. Let's see. Okay, interesting. So they wrote a check. They said, all right, for each query, we're going to do a check. Okay, fine. That's fair. And the check is the length, min value, max value. Okay. For each of these. So it does do a linear time search over the numbers. It's a min value and a max value. Does a check to see if there's a modular, so terminate early check. Then it gets the difference. D0, return true. Another terminate early check. Visit. So it does loop directly through and gets this norm. Oh, I see. Oh, interesting. So they created, so I did do it in linear time. Okay, it's faster. Yeah, so what they did was basically create a vector booleans that checks whether or not a particular number has been visited yet. And they actually used the norm, which would be they normalized the values. So the arithmetic sequences aren't that large, which means that this set can be kind of small on the smaller side. It's actually the number of arithmetic values is not that large. Okay, that's a clever way to do it. So it's this kind of like linear time. I would say linear time to process those numbers. But the basic idea would be okay, so you could normalize using the minimum value. You could take the difference between I think the way they did it was that you take the difference between your current value and the minimum value, and then you divide by the differential, and that's going to give you a normalized value, which basically tells you how many times you added d to get to that point. So every element in that arithmetic sequence is going to have sort of a unique normalized value. And pretty much if there's a repeat of any normalized values, then you return false. Or if any of those values are not normalized, cannot be normalized. In other words, if you divide by d and you get something that's a remainder, then you also return false. So an arithmetic sequence is going to have every one of those normalized values represented exactly once. That's a pretty interesting way of doing it. I like that. I didn't think of that. That's a lot faster. Excuse me. It's pretty good. It's clever. I was thinking that like there's maybe some way to do this, but I didn't think of it quickly. But yeah, using it's not really a frequency map. It's more of just it's not exactly a set either. It's if you normalize the values and then use a vector of booleans, you can check that those normalized values don't appear more than once, and that all the values can be normalized. That's a clever approach. I like that. Okay, so let me take a break. It's been almost 6 hours here. Also, let me see. Clever approach. I like that. Okay, so it's been almost 6 hours here. Yeah, I'm just looking to see if the stream's not getting enough data. Buffering. It's buffering now. All right. Let me wait for it to stop buffering before I stop. That's an interesting question. I mean, that's all right, I suppose. So yeah, thank you all for watching. I'm gonna get going, I think. I'm not gonna leave. I think I'm just gonna take a break for a little bit and then go do some other things. Okay, the stream is come back now. It's all right. That's good. It's a bit of a grind so far. Yeah, all right, let me stop here. I'm gonna stop here and then I think I'll go ahead and take a break for a few hours, maybe an hour or two, and then come back and do a few more hours. I'll try to do I was thinking about wanting to do like 8 hours today, but that would be cool. So yeah, thank you again for watching, hanging out, saying hello. I appreciate it. Let me, I think I'll just stop here. Just stop. If you like the stream, don't forget to follow, like the video, all that stuff, and, or to subscribe rather.